Boötes void is a named region of unusually low galaxy density identified through three-dimensional galaxy surveys in the direction of the constellation Boötes. The stars that define Boötes on the night sky belong to the Milky Way and sit at distances of tens to hundreds of light years. The void lies vastly farther away in the realm where galaxies are mapped not by eye, but by catalogues of positions and redshifts. Its identity comes from the way galaxies populate space in the nearby universe. When thousands to millions of galaxies are plotted in 3 dimensions, they do not fill the volume uniformly. They trace a cosmic web of filaments and sheets, leaving large cavities where the density of luminous galaxies is much lower than average. The Boötes void stands out as one of the most prominent of these cavities in the local cosmic web because of its large apparent scale and its deep deficit in bright galaxy tracers. Locating the void is an exercise in coordinate systems and in definitions. On the sky, the void corresponds to a broad patch in the Boötes direction. Along the line of sight, it corresponds to a range of distances measured through redshift, the stretching of galaxy light to longer wavelengths due to cosmic expansion. A galaxy's redshift is measured from its spectrum, where recognizable features shift in wavelength by an amount that encodes recession speed. For the distances relevant to Boötes, redshift provides a reliable distance proxy, though not perfect because each galaxy also has a smaller motion relative to the general expansion called peculiar velocity. In void work, this means that the 3-dimensional map is made in redshift space, where line-of-sight positions include both expansion
position marking
and
the
motion.
rhythms of life,
The Boötes
weather,
void is
and time
robust in the
itself.
sense that it appears across surveys and remains a large underdensity even when different methods are used to smooth the data or to define the void boundary. Yet its exact center radius and volume depend on choices which galaxy sample is used. What brightness threshold defines completeness, and what void-finding algorithm defines the connected underdense region. The void scale is commonly described as hundreds of millions of light-years across, but this number is not a single immutable value. It can refer to the diameter of the deepest core, or to a broader connected underdensity that includes adjacent underdense regions.
The intense heat
In
of Sirius
practice,
A
analysts
burns
define
at
a
blistering
density threshold
9,940
relative to the mean density of a
Kelvin.
chosen tracer sample, and then find the largest connected region that stays below that threshold. This yields a void that can be mapped with a center and an effective radius.
The life cycle of
Another
Sirius
approach
A
identifies
mirrors that of all
maximal
stars.
empty
A
spheres, the
constant
largest
burn of
spheres,
fusion.
that contain no galaxies above a certain brightness. This can highlight the
As
emptiest parts of a
Sirius A
region
burns
and can
brightly,
produce large sphere sizes in
the
particularly
quiet
empty
existence of
volumes.
Sirius B,
Different
a
approaches
remnant of its
emphasize
former
different
self,
aspects of the
offers a
same
contrast.
underdensity. For a named void like Boötes, the name persists even as definitions evolve, which can create confusion when people compare numbers across decades of literature. A careful description
dual
therefore
nature
always
of the
states
Sirius
which
system,
tracer and
a
method
living
define the
star and a
void.
cool.
The surrounding environment helps anchor the location. The void is not an isolated bubble. It sits amid walls and filaments that form the nearby cosmic web. These higher density structures outline where the underdensity begins to rise. The void boundary is therefore a zone rather than a sharp surface. It is measured by how the galaxy density increases as one moves outward from the core. If the void is measured using only bright galaxies, the boundary can look sharper, because bright galaxies are strongly clustered and can be absent from the interior almost entirely. If the void is measured using fainter galaxies, the boundary can look softer, because faint galaxies populate lower density regions more readily. This is why the void's apparent emptiness and size depend strongly on which galaxies are included. The same physical region can look different when traced by different populations. The phrase hidden anomaly implies a specific feature within this mapped region that appears inconsistent with expectations. Before any such feature can be evaluated, the region must be fixed in survey terms so that the relevant volume is clear. That includes specifying the angular footprint, the redshift interval, and the tracer completeness. Without this, an anomaly can be a moving target because shifting the void boundary can move an object from inside to outside, or change the baseline density against which it is judged. In the Boötes context, many apparent surprises arise because an object is described as being deep in the void when it is actually near a boundary filament under a different definition, or because the void appears nearly empty in a bright galaxy sample, while a fainter sample would show more inhabitants. Fixing the region means committing to a definition that can be replicated in simulations and in independent surveys. Another essential part of locating the void is acknowledging the role of survey geometry and masking. Surveys do not observe the sky uniformly. Bright stars, dust, and instrument footprints create gaps. A robust void location is one that does not coincide with a major unobserved region, and that persists when masks are applied correctly. The Boötes void has been recognized across multiple survey efforts, which supports its reality as a genuine underdensity rather than a pure observational gap. Yet the details of its internal inventory, the sharpness of its boundary, and the identification of substructure can still be affected by varying survey depth and completeness across the area. Therefore, even at the stage of locating the void, one begins to see how a hidden anomaly could be produced by non-uniform sampling, if not handled carefully. In a calm model aligned, framing the Boötes void as a large nearby underdensity in the luminous galaxy distribution, defined in redshift space outlined by surrounding filaments and walls, and measured with a definition that depends on tracer selection and algorithm choice. This is the stable outer frame. Within it, any specific claim of an anomaly must be attached to a specific observable within that same frame, such as an unexpected concentration of galaxies, an unusual galaxy property distribution, an absorption signature of unexpectedly dense or enriched gas, or a gravitational or dynamical signal inconsistent with the inferred mass profile. The next step is to define precisely what anomaly means in this setting, because without a clear definition, confusion is guaranteed, and the phrase "scientist confused" becomes a description of ambiguity rather than a description of evidence. In the setting of a large cosmic void, an anomaly is not a feeling of surprise and not a single unusual object. It is a measurable deviation that persists after the measurement is defined clearly, after known systematics are addressed, and after the expected statistical spread of outcomes is accounted for. This matters because the Boötes void is an extreme environment by construction. Extremes naturally produce outliers. A void also contains few galaxies, which makes random fluctuations large in fractional terms. These two facts together mean that many apparent anomalies are expected appearances rather than failures of models. Therefore, the first step is to define anomaly as a discrepancy between an observed quantity and the predicted distribution of that quantity under a specified model and a specified observational selection. The specified model in this context has layers. There is the cosmological framework that predicts the distribution of matter, the evolution of density fluctuations, and the statistical properties of voids in the mass field. Then there are the prescriptions that map mass into observable traces such as galaxies and absorption systems through galaxy formation and gas physics. An anomaly can be in either layer. A cosmological anomaly would mean the mass under density, the size distribution, or the dynamics of the void are inconsistent with the cosmological predictions given the surveyed volume. An astrophysical anomaly would mean the galaxies or gas within the void have properties or abundances inconsistent with the galaxy formation and gas modelling layered on top of the cosmology. The second type is more common because baryonic physics is complex and uncertain, especially in low-density regimes. Distinguishing these layers is essential because the phrase "scientist confused" can arise when one person is thinking of a cosmological anomaly and another is thinking of an astrophysical modelling gap. A measurable anomaly must be anchored to an observable. For Boötes, the candidate observables fall into a few classes. One class is galaxy number density as a function of position, such as the depth of the void in a volume-limited bright galaxy sample. Another class is the abundance of specific galaxy types inside the void, such as gas-rich dwarfs, low-surface brightness galaxies, or unusually massive systems measured relative to expectations for the same tracer selection. Another class is the distribution of galaxy properties, such as star formation rates, metallicities, and gas fractions at fixed stellar mass. Another class is absorption line statistics, such as the frequency and strength of hydrogen and metal absorbers along sightlines through the void. Another class is gravitational and dynamical signals, such as weak lensing profiles, or redshift space distortion signatures that constrain the mass deficit and velocity field. Each observable has its own measurement pipeline and its own dominant uncertainties. An anomaly definition must specify which pipeline is used because a mismatch can be created by pipeline differences as easily as by new physics. Once an observable is chosen, the next requirement is a matched baseline. A void is usually identified in a particular survey with particular selection limits. Model predictions must be constructed to match those limits. This is typically done through mock catalogues drawn from simulations. The simulation provides a mass field consistent with the cosmological model. A galaxy population is assigned to halos through a method that reproduces observed galaxy clustering and luminosity functions.
The life cycle
the mock
of
is then
Sirius
cut
A
by the
mirrors
same
that of all
magnitude
stars.
limit, the same
A
sky
constant
mask,
burn
the
of
same
fusion.
redshift completeness, and the same measurement errors as the real survey.
As Sirius
The void
A
finder is
burns
then applied to the
brightly.
mock in the same way as to the data.
The quiet existence
The result
of
is a
Sirius
distribution
B,
of void
a remnant
properties
of
and
its
interior
former self,
observables that is
offers a
directly
contrast.
comparable. An anomaly exists only if the observed value lies outside the expected distribution, by a margin larger than can be explained by uncertainties and reasonable
The
variations in
dual
modeling
nature of the
choices.
Sirius system,
This leads to
a
the
living
importance
star
of
and a
statistical
cool-
language. In a universe of enormous volume, rare structures occur. A void like Boötes can be rare and still expected. Therefore, a claim that something is impossible under the model must account for the survey's effective search volume and the fact that the void itself may have been identified as the most extreme feature in that volume. This is the look elsewhere effect. If one scans a large survey and then names the most prominent void, the relevant baseline is the distribution of the most extreme voids in comparable surveys, not the distribution of typical voids. A failure to use the correct baseline can convert an expected extreme into a seeming anomaly. Anomaly definitions must also account for the difference between the mass field and bias traces. A void can be extremely empty of bright galaxies while being only moderately underdense in mass. This is expected because galaxies form preferentially in higher density regions, and because bright galaxies require massive halos that are rare in void interiors. Therefore, a claim that Boötes is too empty must specify whether the claim is about bright galaxies or about mass. If it is about bright galaxies, the model likely predicts such emptiness given bias. If it is about mass, the claim is stronger but also harder to measure. Lensing and dynamics become relevant here. Without them, a mass anomaly
Despite
claim
its
cannot be
brilliance,
supported.
Sirius
Another
light
requirement
travels
is
across
robustness
vast
to
void.
reasonable changes in definition. If a claim of anomaly disappears when one changes the void definition slightly, such as altering the density threshold or the tracer luminosity cut, then the claim is not robust. In contrast, a claim that persists across definitions and traces is more compelling. For example, if the void remains unusually empty in both bright and faint samples, and if lensing suggests an unusually deep mass deficit, the case for a mass anomaly strengthens. If the anomaly is a single galaxy property, extreme robustness means verifying the measurement with multiple calibrations and comparing to matched control samples. The phrase "scientists confused" can also reflect the boundary between what is known and what is uncertain. In void studies, uncertainties are often large. Weak lensing signals are small, Absorption line interpretations depend on ionization modeling. Star formation and metallicity estimates depend on
Ancient
calibration.
cultures saw Sirius as a
Sparse
guide,
sampling
its position
amplifies shock
marking the
noise.
rhythms of life,
In this
weather,
setting,
and
different
time
analyses
itself.
can legitimately yield different conclusions.
Though Sirius B
Confusion
is
can
invisible
therefore
to the
arise
naked
from
eye,
incomplete
it
data
shapes the
rather
system's
than from a
balance.
true contradiction. A disciplined anomaly definition requires explicit uncertainty, quantification, and clear statements of what is constrained and what remains uncertain without speculation. Within this framework, a hidden anomaly in Boötes could mean a statistically significant excess of certain absorbers in the core, suggesting unexpectedly dense or enriched gas. It could mean an interior halo population inferred from dynamics that is richer than expected. It could mean a mass
The
profile
intense
inferred
heat
from
of
lensing
Sirius
that is
A
deeper than
burns at a
predicted.
blistering
Or it could mean a population of
9,940
void
Kelvin.
galaxies with properties outside the predicted range. Each is testable in principle. Each requires different data and different baselines. The role of this
The
definition
life
step is
cycle
to
of
prevent
Sirius
the
A
narrative from
mirrors
drifting.
that of all stars.
An anomaly is a
constant
broken
burn of
expectation, not a dramatic-sounding observation. With anomaly defined as a matched robust
As
discrepancy,
Sirius A
the next
burns
inward
brightly,
step is to describe how the void itself
the
is
quiet
identified in
existence
data,
of Sirius B,
because any anomaly
remnant
claim
of its
depends on
former
the
self,
boundary and membership
offers a
assignment.
contrast.
The method of void finding determines what counts as inside, what counts as outside, and where the core lies. If those definitions are unstable, the anomaly can be an artifact of
The
classification
dual
rather
nature
than a
of the
property
Sirius
of the
system,
region.
a living star
Identifying the
and a
Boötes
cool
void in observational data is an exercise in reconstructing a three-dimensional density field from a sparse set of biased traces. The void is not seen directly. It is inferred from where galaxies are, and equally where they are not under conditions where the survey's limitations must be woven into the definition. The next inward region is therefore the methodology of void finding and membership assignment, because the meaning of any hidden anomaly depends on the stability of the void's boundary and the credibility of the claim that a given signal originates in the void interior rather than in a boundary structure or a sampling artifact. The starting point is a galaxy redshift catalogue. Each entry has a position on the sky, a measured redshift, and observed properties such as brightness and colour. From these one constructs a three-dimensional distribution in redshift space. Because galaxies are sparse on the scale of the void, analysts typically smooth this distribution to estimate a continuous density field. Smoothing can be done by placing a kernel around each galaxy, by constructing a tessellation that partitions space according to nearest neighbours, or by counting galaxies in a grid and applying a smoothing filter. Each method has trade-offs. A fixed grid can blur thin filaments. A nearest neighbour method can be
Despite its
noisy where
brilliance,
galaxies are
Sirius
sparse.
light
A
travels across
tessellation
vast
method
void.
can adapt to local density, but can be sensitive to edge effects and survey masks. In void studies, these choices matter because a void is defined by low density, precisely where noise and edge effects are most pronounced. Once a density field is estimated, a void can be defined in two broad ways. One way is threshold-based region finding. A density threshold is chosen,
Sirius
often
A's
expressed
fusion
as a
creates
fraction of
immense
the
amounts
mean
of
density
energy,
of the tracer
radiating
sample.
light and heat across the
Regions
cosmos,
below the
shaping the
threshold are then
galaxy around it.
identified and connected under dense regions are grouped. The largest or deepest region within a particular area may be labelled as the void. The second way is sphere-based void identification. One searches for maximal empty spheres, the largest spheres that contain no galaxies above a chosen luminosity threshold. These spheres can be used to define the void core. Multiple spheres can overlap and be merged to define a larger void region. The sphere method emphasizes
Ancient cultures
emptiness in
saw
a simple
Sirius as a
geometric
guide,
way.
its
It
position
is
marking the
intuitive
rhythms
but
of
can
life,
fragment a
weather,
complex
and time
underdensity
itself.
into multiple spheres, or
Though
conversely
Sirius
can
B
stitch
is
regions
invisible
together
to the
depending
naked
on
eye,
overlap
It
criteria.
shapes the
A
system's
third
balance.
family of methods uses watershed algorithms. In this approach, the density field is treated like a landscape. Under dense regions correspond to basins. The algorithm identifies local minima and then grows basins outward until they meet at ridges defining void boundaries at density ridges. This method naturally produces a hierarchy of voids and subvoids. It is well suited to the cosmic web's nested structure. The boundaries it produces depend on the smoothing scale and the tracer density, and in
The
sparse
intense heat
regions
of
the
Sirius
minima
A
can be
burns at a
influenced by shot
blistering
noise.
9,940
Yet when applied to large
Kelvin.
surveys and calibrated with simulations, watershed methods can produce robust statistical void catalogues. For a named void like Boötes, a watershed
cycle
method
of
may
Sirius
reveal
A
that the
mirrors
region
that of
contains
all
multiple
stars,
nested
a
basins,
constant burn of
and that
fusion.
the named void corresponds to a higher level merged structure. Membership assignment
As
is the
Sirius
practical
A
bridge between
burns
void
brightly,
finding and anomaly claims.
The
An
quiet
object is said to be
existence of Sirius
inside
B,
Boötes if its
a
coordinates
remnant
fall
of its
within the
former
void
self,
region,
offers
as
a
defined by
contrast.
the chosen method. This seems simple, but it carries subtle issues. First, the void is identified in redshift space. Peculiar velocities shift objects along the
The
line of
dual
sight.
nature of the Sirius
Therefore, an
system,
object's
a
redshift
living
space
star
position
and a
can
cool
place it inside, when its real space position would place it outside. Second, the boundary is a zone of rising density with boundary filaments and sheets. Thin structures can intrude inward. A galaxy can be inside the void volume while residing on a thin filament that is physically connected to the boundary. In environmental terms, such a galaxy is not in the deepest void interior. Therefore, many analyses supplement geometric membership with local density measures. A galaxy might be labelled as a void core galaxy only if it lies below a local density threshold, computed within a smoothing radius, and also lies within the void region. This reduces contamination by boundary intrusions and yields a cleaner sample for studying void galaxy properties. The choice of tracer strongly influences void identification. If one uses only luminous galaxies, the tracer density is low and the voids appear larger and deeper. If one uses fainter galaxies, the tracer density increases and the voids can fragment into smaller subvoids. For Boötes' early identification used relatively bright galaxy samples, contributing to the dramatic impression of emptiness. Modern deeper surveys can reveal more galaxies within the region, potentially altering the void boundary under a given threshold. This does not mean the mass under
Despite its
density
brilliance,
changes. It
Sirius
means the
light
tracer
travels
reveals
across
more of the
vast
underlying
void.
structure. Therefore, any anomaly claim must state which tracer defines the void, because the location of the core and the boundaries can shift. Survey geometry and masks are embedded in void finding through the use of random catalogues and boundary handling. A robust method accounts for the survey footprint by comparing observed galaxy density to an expected density derived
Sirius
from the
A's
selection
fusion creates
function.
immense amounts of
In
energy,
practice, this
radiating
often
light and
means
heat across the
constructing a random
cosmos, shaping
distribution
the
of
galaxy
points that
around it.
follows the same angular coverage and radial selection as the survey, then using it to correct densities. Some void finders incorporate the mask directly, while others require explicit boundary padding or periodic boundary conditions in simulations. Mishandling the mask can create spurious voids or distort boundaries. For a named void, a simple but powerful check is to verify that the void is recovered in multiple surveys with different masks. If it is, the void is less likely to be an artifact.
Ancient cultures saw
For
Sirius
internal
as a
structure
guide,
and anomalies,
its
one
position
must
marking
also
the rhythms
verify
of
that the
life,
internal
weather,
features do
and
not
time
align
itself.
with depth variations or masked
Though
zones.
Sirius
The smoothing
B
scale is
invisible
another
to the
key
naked
parameter.
eye, it
A
shapes
void
the
defined
system's
on a
balance.
smoothing scale comparable to tens of millions of light years captures the large scale under density. A void defined on a smaller scale can be dominated by shot noise in sparse regions and can identify many small empty pockets. For Boötes, whose name refers to a large feature, the relevant smoothing is large. Yet an anomaly claim might concern a smaller scale feature, such as a cluster of galaxies or a filament inside the void. To evaluate such a claim, one must distinguish between the large-scale
The
void
intense
definition
heat of Sirius
and the
A
small-scale
burns at a
structure
blistering
embedded within it.
9,940
A small-scale
Kelvin.
over-density within a large-scale under-density is expected. The anomaly would be if the small-scale overdensity is too strong or too common relative to model
The life cycle
expectations
of
for
Sirius
underdense
A mirrors
environments.
that of all stars.
This methodological
A constant
layer
burn of
explains why
fusion.
scientists can appear confused. Different teams can use different void definitions,
Sirius
tracer
A burns
thresholds,
brightly.
and smoothing scales, producing
The quiet
different boundaries
existence
and
of
different
Sirius
lists of
B,
interior
a
galaxies.
remnant of its former
A
self,
finding that seems
offers a
deep
contrast.
inside under one definition may be peripheral under another. A density profile can appear steep under one tracer and shallow under another. Without explicit methodological
The
alignment,
dual nature
comparisons
of the
become
Sirius
ambiguous.
system, a
The
living
remedy
star
is to
and a
treat the
cool
void definition as part of the measurement, and to require that model comparisons and anomaly statements use the same definition. With the void identification process laid out, the next inward step is to examine how completeness and hidden galaxy populations change the apparent emptiness and can create or dissolve the impression of an anomaly. This involves magnitude limit surface brightness, bias, and the role of alternative tracers such as neutral hydrogen, because in a void, the difference between what exists and what is seen can be especially large. A void is defined by what is missing from a catalogue, so completeness is not a technical side issue, but the foundation of the measurement. The next inward region is therefore the set of ways a galaxy population can be present in the Boötes void, while remaining hidden from the surveys that define the void, and the ways those hidden populations can manufacture the impression of an anomaly. The central idea is that there is a difference between a region that contains little mass and a region that contains mass but lacks luminous, easily detected tracers. In void environments, this difference can be especially large because the halos that exist are typically low mass, and low mass systems are the most vulnerable to detection limits and to the suppression of starlight. The most familiar completeness limit is a magnitude limit.
Despite its
An
brilliance,
imaging survey
Sirius
detects
light
objects down to a
travels across
minimum
vast
brightness.
void.
Spectroscopic follow-up then measures redshifts for a subset. A magnitude limit can be translated into an intrinsic luminosity limit only within a specified distance. This is why void studies often use volume-limited samples, choose a maximum distance and a minimum intrinsic brightness, so that any galaxy brighter than that intrinsic limit would be detectable across
Sirius
the
A's
survey.
fusion creates immense
Within
amounts
that
of
volume,
energy,
the sample is
radiating
close to
light and
complete
heat
for that
across the
class.
cosmos,
The
shaping the
trade-off
galaxy
is that
around
the
it.
sample excludes faint galaxies. In the Boötes void, where faint galaxies may dominate a bright volume, limited sample can portray the void as nearly empty, even if many faint dwarfs exist. This effect is expected. It can, however, be misinterpreted as a physical anomaly if one treats the bright galaxy emptiness as equivalent to mass emptiness. The correct interpretation is that the chosen tracer is absent, not necessarily that all structure is absent. Surface brightness is
Ancient
a deeper and
cultures
often
saw
more
Sirius as a
decisive
guide,
completeness limit.
its position
A
marking the rhythms
galaxy
of
with
life,
the same
weather,
total
and time
luminosity can be
itself.
either compact and high contrast,
Though
or diffuse
Sirius B
and low
is invisible
contrast.
to the naked eye,
Detection
it
algorithms
shapes the
rely on
system's
contrast
balance.
against the sky background. A diffuse galaxy can fall below detection even if its total light would place it above a nominal magnitude limit. Low surface brightness galaxies are especially relevant in void environments because reduced interaction rates and slower star formation can produce diffuse stellar distributions and faint outer disks. In addition, small galaxies with low metallicity can have fewer bright stars and lower dust, changing their light profiles. If the Boötes interior hosts a
The
substantial
intense heat of
population of
Sirius A
low-surface
burns
brightness
at a
dwarfs,
blistering
then optical catalogues can
9,940
undercount galaxies severely. This can create the impression of an unusually deep void, and can also affect claims of anomalies in galaxy properties, because the detected sample becomes biased
The
toward
life
the
cycle
rare
of
higher
Sirius
surface
A
brightness
mirrors
systems.
that of all stars.
A hidden
constant
population
burn of
alters
fusion.
not only counts, but also the inferred typical properties of void galaxies.
As
Spectroscopic
Sirius A
incompleteness
burns
adds another
brightly.
layer. Even when a galaxy
The
is
quiet
detected in
existence
imaging,
of
obtaining a
Sirius B,
redshift can
a
fail for
remnant of
diffuse
its
or
former
faint
self,
objects.
offers a
Spectra
contrast.
can have low signal to noise, emission lines can be weak, absorption features can be hard to measure. Incomplete redshift sampling can create a pseudo-void in three-dimensional maps
The dual
because
nature
galaxies
of the
without
Sirius
redshifts
system,
are
a
effectively
living
absent from
star
the
and a
redshift
cool-
space distribution. Modern surveys quantify spectroscopic completeness and apply weights, but the weights assume that missing redshifts are random within certain categories. If missingness correlates with low surface brightness or with specific environments, the correction can be imperfect. In the Boötes region, if faint diffuse galaxies are systematically less likely to have measured redshifts, the void can be overstated. The remedy is targeted spectroscopy for void candidates, and the use of alternative redshift methods where possible. Foreground effects can also hide galaxies. Milky Way dust extinction dims background galaxies. If extinction is higher in part of the Boötes direction, more galaxies fall below detection limits. Surveys correct for extinction using dust maps, but residual errors can remain. This is unlikely to create a void as large and deep as Boötes by itself, but it can contribute to the appearance of sharp boundaries and can affect faint end counts. Bright stars can also create halos and scattered light that obscure faint galaxies, creating local holes in imaging. These holes can cluster in patterns depending on star distribution. Proper masking accounts for this, but it can reduce effective survey area and complicate
Despite
void
its
boundary
brilliance,
definitions.
Sirius light
Alternative
travels
traces
across
reveal
vast
different
void.
hidden populations. Neutral hydrogen surveys can detect gas-rich galaxies that are optically faint or diffuse. In a void where gas stripping is weak, low-mass galaxies may retain significant neutral hydrogen even if their starlight is faint. Therefore, radio surveys can uncover galaxies that optical surveys miss. If such galaxies are abundant in Boötes, the
Sirius
void's
A's fusion
perceived
creates
emptiness
immense
in
amounts of
baryons
energy,
and in
radiating
potential
light
star
and heat across
formation
the
fuel
cosmos,
changes.
shaping the galaxy
Yet
around
radio
it.
surveys have their own selection biases. They favour gas-rich systems and can miss gas-poor dwarfs or quenched galaxies. A combined optical and radio view is therefore necessary. Similarly, infrared surveys can detect dust heated by stars, but void galaxies may have low dust content, making infrared faint. Ultraviolet surveys can detect young stars, but dust corrections and background subtraction can be challenging. Each tracer sees a
Ancient
different
cultures
slice
saw
of the
Sirius as a
galaxy
guide,
population.
its position
Hidden
marking the
populations
rhythms
are
of
not only a
life,
detection
weather,
issue,
and
but
time
also a
itself.
physics issue. In void interiors,
Though
many halos may
Sirius
be
B
below the
is
threshold
invisible
for
to the
sustained
naked
star
eye,
formation
It shapes
due
the
to the
system's
ionizing
balance.
background. Such halos may host very few stars and thus be truly faint. Some may host none, making them dark halos. These dark halos contribute to mass but not to light. If one
Sirius
equates the
thickness
galaxy
makes
catalogue
us
to the matter field, the void appears more extreme than it is. This can lead to claims of cosmological anomaly. The correct baseline expects a population of dark or nearly dark halos in voids. The question becomes whether the abundance and distribution of faint galaxies
intense
implied by
heat of
observations
Sirius A
match the
burns at a
predictions for
blistering
halo occupation.
9,940
If there is a
Kelvin.
mismatch, it is more likely to indicate a gap in galaxy formation modelling, such as how reionization and feedback suppress star formation, than a failure of cosmology.
The life
Completeness
cycle of
also shapes
Sirius
the
A
perception
mirrors
of
that of
internal
all
structure.
stars. A
In a
constant
sparse
burn of
catalogue,
fusion.
a few detected galaxies may appear as a filament or group. If many
As
faint
Sirius
galaxies
A
are missing, the
burns
internal
brightly,
structure map is incomplete and
The
can
quiet
exaggerate
existence
apparent
of Sirius
coherence.
B, a remnant of
Conversely,
its
adding
former
faint
self,
galaxies
offers
can
a
reveal a more
contrast.
continuous distribution. Therefore, claims of a hidden anomaly based on internal structure must be tested against deeper catalogues. An internal filament that persists as more
The
galaxies
dual
are
nature
added is
of the
more likely
Sirius
real.
system, a living
A
star
filament that
and a cool
dissolves is likely an artifact of sparse sampling. This layer clarifies why confusion can persist in discussions of Boötes. Different surveys and different tracers see different populations. A bright galaxy map shows dramatic emptiness. A deeper map shows more inhabitants. A radio map shows gas-rich systems. Each can be framed as revealing something unexpected if the baseline expectation is not matched to the tracer. The calm scientific approach treats completeness as part of the definition of the void and treats hidden populations as expected in low-density environments. With these factors acknowledged, the next inward step is to re-establish the outer context that outlines the void, the surrounding walls and filaments, because the contrast between interior and exterior depends on the same completeness issues, and because the boundary structures provide the local baseline against which any anomaly inside is judged. The Boötes void is defined by its contrast with the surrounding cosmic web, and that surrounding structure is the local baseline against which any claimed anomaly must be judged. The next inward region is therefore the set of walls and filaments that border the void, because these structures not only outline the void geometrically, but also shape the observational and physical context for what can appear unexpected inside. A void interior is not interpreted in isolation. It is interpreted relative to neighbouring regions at similar distances where galaxy density, halo mass, and gas conditions are more typical. If the surrounding web is unusually strong or unusually arranged, it can amplify the perceived extremeness of the void. If the boundary is defined by a sparse tracer, it can appear sharper. If the survey coverage is uneven, the boundary can appear displaced. Understanding the outer web is thus part of making sense of the interior. In three-dimensional galaxy maps, the region around Boötes shows higher density concentrations that form a partial enclosure. These concentrations are not a spherical shell. They are the interconnected filaments and sheets that characterize the cosmic web. Filaments are elongated channels of higher density dark matter and baryons where galaxies align and where gas flows toward nodes. Sheets are broader planar structures that separate neighbouring voids. Nodes are the densest junctions where groups and clusters form.
Ancient cultures
the void
saw Sirius
sits
as a
among
guide,
these features,
its position
and its
marking the
boundary
rhythms
is the
of
transition
life, weather,
zone where the
and time
density
itself.
rises from very low in the interior to higher in the web.
Is invisible
This
to the naked
transition is
eye.
gradual and
It shapes
uneven.
the system's balance.
Some directions from the void center encounter strong filaments and walls quickly. Other directions open into broader, underdense regions or into less pronounced walls. This anisotropy is expected because the cosmic web itself is anisotropic. The physical role of boundary structures is tied to void dynamics. Over cosmic time, matter tends to flow away from the underdense region and toward denser regions. This flow contributes to the growth of filaments and walls at the void's edges. In some cases, this leads
The
to a
intense heat of
compensating region
Sirius A
over dense
burns at a
shell-like
blistering
enhancement that partially
9,940
balances the
Kelvin.
void's mass deficit. Whether the ridge fully compensates depends on the void's embedding in the larger scale density field. If the void is part of a broader underdensity, the
The life
compensation
cycle
may
of
be
Sirius
incomplete.
A mirrors that of
For
all
Boötes,
stars.
a reasonable
A constant
expectation
burn
is
of
that some
fusion.
local ridge exists in the galaxy distribution, because the boundary is visibly traced by
As
surrounding
Sirius A
structures,
burns
but the
brightly.
degree of mass compensation
The
remains
quiet existence
uncertain
of
without
Sirius
mass-sensitive probes.
A remnant of its former
The presence or absence
offers a
of a strong
contrast.
ridge matters for claims of anomaly, because it affects expected outflow velocities and potential integrated gravitational effects. The observational role of boundary
The
structures is
dual
equally
nature
important.
of the Sirius
The
system.
boundary
a
is where
living
galaxy
star and a
density is
cool-
higher, so it is better sampled and measured more precisely. This means density profiles, boundary shapes, and internal membership are often anchored by boundary galaxies. If boundary sampling is biased, the inferred void geometry can be biased. For instance, if the survey depth varies and is shallower near part of the boundary can appear to recede outward because fewer galaxies are detected there. If masking removes part of a filament, the void can appear to extend into that masked region. Therefore, reliable boundary mapping requires uniform coverage and explicit mask handling. The fact that Boötes has been identified in multiple surveys reduces the likelihood of a purely geometric artifact, but detailed boundary features can still be sensitive to coverage. Boundary structures also influence the classification of interior objects. Filaments can intrude inward, creating narrow corridors of higher density within the nominal void volume. Galaxies on these intrusions can be mistakenly labelled as interior anomalies. For example, a relatively massive galaxy, or a compact group, might appear deep inside if one uses a broad void definition, yet the galaxy may actually reside on a thin filament connected to the boundary. From the standpoint of local environment, that galaxy is not a representative void core system. Therefore,
Despite
any
its
claimed
brilliance,
anomaly involving an
Sirius
object
light
within
travels
Boötes
across
must
vast
examine the
void.
object's local density and connectivity, not merely its inclusion within a global void boundary. A galaxy can be inside the geometric void and still be in a locally filamentary environment. Models predict this. Treating it as unexpected can be a classification error. The boundary also provides the appropriate comparison population for galaxy properties. Galaxies
Sirius
just
fusion
outside the
creates
void
immense
in
amounts of
surrounding
energy,
filaments and
radiating
walls
light and
can be
heat across
compared
the
to
cosmos,
galaxies
shaping
inside
the
to measure
galaxy around it.
environment-dependent shifts. Because the boundary and nearby exterior are at similar redshift, this comparison minimizes observational biases related to distance. If an anomaly claim involves void galaxies being unusually active, unusually metal-poor or unusually gas-rich, the most informative test is to compare those galaxies to boundary and exterior galaxies of similar stellar mass and observational completeness. Differences then reflect environment rather than distance. This approach
Ancient
also helps
cultures saw
disentangle
Sirius as a
selection
guide,
effects.
its position
If the
marking
void
the
sample
rhythms
is
of life,
missing low
weather,
surface
and
brightness
time
galaxies,
itself.
but the exterior sample is not.
Though
The
Sirius
comparison
B
can be
is
biased.
invisible to the naked
Uniform
eye,
selection
it shapes the
and
system's
careful
balance.
completeness modelling are therefore essential. Gas physics also changes across the boundary. Filaments and walls contain denser gas that can be heated by compression and shocks. They are more likely to host metal-enriched gas due to higher galaxy density and more frequent outflows. Therefore, absorption line statistics should show stronger and more frequent absorbers near the boundary than in the core. If an anomaly claim involves unexpectedly strong absorption in the core, the boundary provides a reference. One asks whether the core
intense heat of
absorbers
Sirius
resemble
A
boundary
burns at a
absorbers in
blistering
strength and metallicity,
9,940
and whether such
Kelvin.
resemblance is plausible given internal filaments or hidden galaxies. Similarly, if the core shows an absence of absorption, one asks whether the boundary behaves
The life
normally,
cycle of
confirming
Sirius
that the
A
measurement is
mirrors that of all
sensitive
stars,
and that the
a
absence is
constant
not a
burn of
data
fusion.
quality issue. The boundary's dynamical role also frames interpretation.
As
The void
Sirius
outflow
A
pattern is
burns
shaped by the
brightly,
mass deficit and by the surrounding
the
mass
quiet existence
concentrations.
of Sirius B,
Nearby
a remnant
overdensities
of
can
its
pull
former
matter,
self,
altering flow
offers a
directions.
contrast.
This can produce asymmetric redshift space distortions. If an anomaly is claimed in dynamics, such as an outflow pattern that seems too strong or too weak, one must account for the
The
surrounding
dual
web's
nature of
influence.
the Sirius
A
system,
void is
a
not a
living star
perfectly
and a
isolated
cool-
system with spherical symmetry. Its velocity field reflects the actual distribution of mass around it. In summary, the surrounding walls and filaments are the outer scaffolding that both defines Boötes and constrains what could be anomalous inside it. They anchor the geometry, provide comparison populations, influence gas and dynamics, and create intrusions that can masquerade as interior anomalies. With this context set, the next inward step is to describe how an extreme void like Boötes forms within the standard cosmological framework, because the plausibility of a truly anomalous void depends on whether its size and depth can arise from known initial conditions and gravitational growth, and on whether the void might be a merged structure rather than a single coherent basin. An extreme void like Boötes forms through ordinary gravitational evolution, acting on the initial density field, but its apparent scale and depth can be amplified by the way under dense regions merge and by the way galaxies trace mass. The next inward region is therefore the formation pathway of a large void within the standard framework, because this pathway sets the baseline for what should and should not cause confusion. If the formation pathway naturally produces large connected underdensities, then a large named void is not inherently anomalous.
Despite
If the
its
pathway
brilliance,
predicts certain
Sirius
correlations
light
between
travels
size,
across
depth, and
vast
surrounding
void.
structure, then deviations from those correlations can be the meaningful place to look for tension. In the early universe, matter is almost uniform, but it contains small fluctuations. These fluctuations are described statistically. Some regions start slightly above average density and some slightly below. Gravity acts more strongly where density is higher. Over time, over-dense regions grow, attracting
Sirius
more
A's
matter
fusion
and forming
creates immense
filament
amounts of
sheets and
energy,
eventually
radiating
clusters.
light and heat across the
Under-dense
cosmos,
regions, by
shaping the
contrast,
galaxy
have less
around it.
gravitational pull. Matter flows away from them toward the growing over-dense structures. The under-dense regions become comparatively emptier as the contrast increases. This is not an active evacuation. It is the passive consequence of the same gravitational processes that build the cosmic web. In simulations, voids are therefore a natural and abundant outcome. A useful way to describe void formation is through relative expansion. All of space expands, but over dense regions expand
Ancient cultures
less,
saw Sirius
because gravity
as a guide,
slows them
its
and
position
can even
marking the
reverse
rhythms of life,
expansion locally
weather,
into collapse.
and time itself.
Under dense regions expand more,
Though Sirius
in the
B
sense that
is
their
invisible
internal
to the naked
separations
eye,
grow closer to
it
the
shapes
background
the system's
expansion rate
balance.
and are less slowed. This differential expansion causes matter to drift outward from the underdense center. Over billions of years, the underdensity deepens, and a boundary region forms where the displaced matter contributes to filaments and walls. The boundary is not an ideal shell, but a network of web structures that intensify relative to the interior. Large voids can arise through two main routes. One route is a large-scale initial under-density, a coherent region that is slightly below
The
average on
intense
a large
heat
scale.
of Sirius A burns
Such
at
a region will
blistering
tend to evolve into a large void.
9,940 Kelvin.
The second route is merging. The density field contains many under-dense basins separated by modest ridges. As evolution proceeds, some ridges become
life
relatively
cycle of
weaker
Sirius A mirrors
compared
that
to
of all
surrounding
stars.
structures,
A constant
and
burn
basins
of
can
fusion.
merge into a larger connected under-density. This merging is gradual and produces a
Sirius
larger
A
void that
burns
contains
brightly.
internal substructure, such
The
as
quiet
residual
existence of
filaments and
Sirius
shallow
B,
ridges that
a
mark the
remnant of
former
its former
boundaries.
self, offers a
This route is
contrast.
particularly important because it explains why a void can appear extremely large when defined by connected underdensities. What is called Boötes may include multiple subvoids that have
The dual
merged
nature
or are
of the
connected
Sirius
through
system,
low-density
a living
channels.
star and a
If so, then the apparent scale can be large without requiring an implausibly large single primordial underdensity. Confusion can arise if one compares such a merged connected void to model predictions for single basins defined differently. The standard framework also predicts correlations between void properties. Large voids tend to have shallower mass underdensities in their cores than small deep voids, because large voids often arise from the merging of multiple basins, and because the mass deficit is distributed over a larger volume. In contrast, the deficit in bright galaxies can remain very strong, because bright galaxy formation is suppressed in low-density environments. This means a large void can appear extremely empty in luminous traces, while being only moderately underdense in mass. This is a baseline expectation. Therefore, a claim that Boötes is too empty must specify whether the emptiness is in bright galaxies, which is expected, or in mass, which would be a stronger claim. If a large void were also extremely deep in mass, that could be more difficult to accommodate depending on the survey volume and the model parameters, but such a claim requires mass-sensitive probes. The evolution of voids is also influenced by the changing expansion history of the universe. At early times, when matter dominates the energy density structure, growth is faster.
Despite
Under
its
dense
brilliance,
regions deepen
Sirius light
relative to the
travels
mean,
across vast
and
void.
matter flows outward more strongly. At later times, dark energy becomes important and slows the growth of structure by accelerating the expansion. This does not erase voids, but it reduces the rate at which contrast grow. A present-day void like Boötes reflects this long history. Its current depth and size are the cumulative result of
Sirius
billions
A's
of years
fusion
of
creates
differential
immense amounts of
expansion and
energy,
matter flow.
radiating light and
Formation
heat
also
across the
sets
cosmos,
expectations
shaping
for
the
what
galaxy
remains
around it.
inside. Even in a large void, small-scale fluctuations exist. Underdense does not mean smooth. The interior is expected to contain a diluted dark matter web with low-mass halos and faint internal filaments. These structures can host a sparse population of galaxies, often low-mass and gas-rich. The presence of some internal structure is therefore expected, and it can look like an anomaly only if one imagines the void as perfectly empty. A genuinely surprising interior structure would be one that implies a large mass concentration, incompatible with the void's claimed underdensity, such as a rich cluster deep in the core. Such cases often dissolve under careful boundary and membership analysis. In addition, galaxy formation physics can amplify void appearance. Because halo growth is slower and halo masses are lower in void interiors, luminous galaxies are rare. Many halos may be below thresholds where gas can cool and form stars efficiently under the ultraviolet background. Feedback from supernovae can also expel gas from shallow halos, reducing starlight. These effects produce a population of faint or dark halos. Therefore, a void can look emptier in starlight than the mass deficit would
Sirius
suggest.
A burns at a
This
blistering
amplification is predicted, but its
9,940
magnitude
Kelvin.
depends on the details of galaxy formation modelling. If Boötes appears even emptier than models predict in a tracer-matched comparison, it could indicate that models overpredict
The life
star
cycle of
formation in
Sirius
void
A mirrors
halos,
that of all
or
stars.
underpredict the abundance of
constant
dark
burn of
halos.
fusion.
This would be an astrophysical modelling mismatch, not necessarily a cosmological failure. This formation pathway clarifies where confusion is legitimate. If different analyses define Boötes differently, one might be describing a merged, connected underdensity, while another is describing the deepest core. If one analysis uses bright galaxies, the void appears extremely empty, while another using fainter galaxies finds more inhabitants. If one compares a connected void to a single basin prediction, the void may look too large. These are definition mismatches, not physical anomalies. A true anomaly would be a persistent mismatch between observed void statistics and the distributions predicted by simulations under matched definitions and selections. With the formation baseline established, the next inward step is to state the standard model baseline for void interiors, more explicitly separating expectations for halos, gas, and galaxies inside a large void like Boötes. This provides a concrete reference against which any claimed hidden anomaly can be evaluated, and it makes clear whether the surprise lies in cosmology and galaxy formation or in measurement. The baseline model for a large void interior is a layered expectation across dark matter, gas, and galaxies, with each layer becoming progressively more selective about what is visible. The next inward region is therefore this baseline interior stated plainly as what standard simulations and well-tested physical reasoning imply should be present inside a void like Boötes when it is defined in a modern survey context. This baseline is the reference frame for any claimed hidden anomaly. If a reported feature lies within the baseline, it is not anomalous, even if it feels surprising. If it lies outside, the question becomes whether the deviation is in the mass field in the baryonic physics or in the observational pipeline. At the mass level, the baseline is that the void is underdense but not empty. Dark matter is expected to form a connected web across the universe. In a void, the web is diluted. The mean density is below the cosmic average, and the amplitude of small-scale structures is reduced. Yet small-scale fluctuations remain. The void interior therefore contains low-contrast filaments and
Sirius A's fusion
nodes.
creates immense
Within
amounts of
these
energy,
nodes, low-mass
radiating light
dark
and heat
matter
across the
halos form.
cosmos, shaping
The
the galaxy
abundance of
around it.
high-mass halos is strongly suppressed. This is a key prediction. A large void should contain very few halos massive enough to host bright galaxies. Instead, it should be dominated by halos at the low-mass end. Many of these halos can exist without hosting luminous galaxies because luminous galaxy formation becomes inefficient. below certain mass and cooling thresholds. The net effect is that there can be many more halos than visible galaxies, especially in a void environment. This is expected and is one reason galaxy maps can make voids look more extreme than the mass field would suggest. The spatial distribution of halos in the void is also predicted to be non-uniform. Halos tend to reside along the faint internal filaments, rather than being scattered randomly. This can lead to alignments of the few galaxies that do form, making internal structure appear more coherent than one might expect. In reality, the coherence is a natural consequence of the underlying density field. The void can also contain subvoids nested under dense basins separated by weak ridges. If the named void corresponds to a merged structure, these subvoids can be present as internal gradients in density. Therefore, the baseline does not predict a single smooth bowl. It predicts a basin with internal texture. At the gas level, the baseline is that most ordinary matter in the void remains in the intergalactic medium in ionized form. The gas is illuminated by the ultraviolet background, which keeps hydrogen and helium ionized over most of the volume.
Mirrors that of all stars.
In low-density regions, recombination is slow, so the neutral fraction of hydrogen is very low, even if the total gas mass is significant. This makes the gas difficult to detect in emission and subtle in absorption. The temperature of the void intergalactic medium is expected to be governed mainly by photoheating and adiabatic cooling. In dense filaments, gas is compressed and shock-heated, producing warmer phases.
The dual nature of the Sirius
In voids,
system,
strong shocks are rarer, so a larger fraction of gas may remain in a cooler photoionized state, though still warm enough that it remains ionized. The baseline also predicts that void gas is on average less enriched with heavy elements than filament gas, because there are fewer galaxies to produce and expel metals. Yet enrichment is not absent. Metals can be transported by galactic winds, and by long-term mixing and internal faint galaxies can contribute locally. Therefore, the baseline predicts low average metallicity with scatter, and it predicts that occasional enriched absorbers can occur along sightlines that intersect internal filaments or halo outskirts. At the galaxy level, the baseline is that the void interior contains a sparse population of mostly low-mass galaxies with properties shaped by isolation and by the difficulty of cooling and forming stars in low-density, low-metallicity conditions. Because high-mass halos are rare, massive galaxies are rare, the galaxies that do exist are more likely to be disk-dominated and gas-rich. They are more likely to be star-forming at some level, because environmental quenching mechanisms common in groups and clusters are absent. However, their star formation efficiency can be low, because the conversion of atomic gas into molecular clouds is less efficient at low metallicity and low density. This can produce galaxies with substantial neutral hydrogen reservoirs, but modest star formation rates. Their chemical enrichment can be slower, yielding lower metallicities at fixed stellar mass compared to denser environment galaxies. Their interaction and merger rates are lower, leading to fewer major merger remnants and fewer large ellipticals. A baseline expectation also includes the role of observational selection. A void defined in a bright galaxy sample will appear very empty, because the baseline predicts that bright galaxies are rare in low-density environments. If the tracer threshold is lowered to include fainter galaxies, the void will contain more detected galaxies, but its density will still be below average because the underlying mass field remains underdense. Therefore, the baseline predicts a void that persists across tracer choices, but with varying apparent depth and structure. A hidden population of low surface brightness galaxies is expected to exist at some level, and it can be revealed only by deep imaging and specialized detection.
Ancient cultures saw
the
Sirius
baseline
as a
also
guide,
expects that
its
radio
position
surveys will
marking the
find some
rhythms of
gas-rich
life,
galaxies
weather,
missed
and time
optically,
itself.
but it does not predict that these will fill the void to normal
Sirius
density.
B is
This
invisible to
baseline
the naked
establishes
eye.
what would qualify
It
as a
shapes the
hidden
system's
anomaly.
balance.
An anomaly in the mass layer would be a mass deficit inferred through lensing or dynamics, that is much deeper or larger than the baseline distribution in simulations for the survey volume. It would be a void whose mass profile is inconsistent with standard initial condition statistics. An anomaly in the gas layer would be a systematic excess of dense or highly enriched absorbers in the core beyond what simulations predict for void environments, or a systematic absence of expected absorption,
The intense
indicating a
heat of
baryon
Sirius
distribution
A burns at a
radically
blistering
different from the baseline.
9,940
An
Kelvin.
anomaly in the galaxy layer would be an overabundance of massive halos inferred from galaxy dynamics or group richness in the deep core, or a galaxy population whose star formation
The
and
life cycle
metallicity
of Sirius A
distributions
mirrors
are
that of all
inconsistent
stars.
with plausible
constant burn
baryonic
of fusion.
prescriptions. A single unusual galaxy or a single absorber is
As
rarely
Sirius A
sufficient.
burns
The anomaly
brightly,
would need to be a pattern. Confusion
quiet
among
existence
scientists
of
often
Sirius
arises
B,
because different
a remnant
observers
of its
focus on
former
different
self,
layers.
offers a contrast.
Someone looking at a bright galaxy map sees extreme emptiness and may talk as if the void is almost a hole in the universe. Someone modelling dark matter sees a moderate underdensity with many
The dual
low-mass
nature of the
halos and sees
Sirius
nothing
system,
paradoxical.
a living star and
Someone
a cool
measuring absorption sees occasional enriched systems and wonders how metals reach the void. Each view is valid within its measurement layer, but the interpretations differ if the baseline is not made explicit. The baseline provides a common language. It says what is expected to exist and how it should appear under different traces. With this baseline in place, the next inward step is to describe the observed galaxy census inside Boötes, under modern understanding focusing on what kinds of galaxies are found, how their distribution relates to internal substructure, and what aspects of the census could plausibly generate claims of a hidden anomaly, without immediately collapsing into selection effects or boundary misclassification. The observed galaxy census inside the Boötes void is the concrete list that anchors most public claims of emptiness and most claims of anomaly. The next inward region is therefore the interior inventory, as it is built from survey data along with the interpretive steps that separate a sparse but expected population from a pattern that might be genuinely puzzling. The census begins with the simplest fact: relative to the surrounding cosmic web, the number of galaxies above standard optical survey thresholds inside the Boötes volume is low. That deficit remains even as surveys improve.
Despite its
What
brilliance,
changes with improved
Sirius
surveys is
light
the
travels
detail.
across vast
More faint
void.
galaxies are found, more low surface brightness candidates are identified, and more gas-rich systems are detected in radio, refining the interior structure without erasing its underdensity. Membership is the first challenge. A galaxy is said to be inside the void if its sky position and redshift place it within the void boundary under a chosen definition. But the boundary is
Sirius
not
A's
sharp,
fusion creates
and
immense
voids
amounts of
contain
energy,
internal
radiating
filaments that
light and heat
connect to the
across the
boundary.
cosmos, shaping
Therefore,
the
a
galaxy
useful
around it.
census distinguishes between galaxies in the deep core and galaxies in the broader interior near the boundary. This distinction can be made with local density estimators such as nearest neighbour distances or smoothed density fields. In Boötes, galaxies that qualify as core members tend to have large separations from their nearest luminous neighbours, reflecting the sparse environment. Galaxies nearer the boundary may still be in underdense space on large scales, but can be locally influenced by filamentary structure.
Ancient cultures saw Sirius
When
as a
claims
guide,
of anomaly
its
arise,
position
they often
marking the
involve
rhythms of
objects that
life,
are not clearly
weather,
core
and time
members under
itself.
strict criteria. The first test is
Though
therefore to
Sirius
evaluate
B
local
is
environment,
invisible
not
to the
just
naked
global
eye,
membership.
It
The
shapes
types of
system's
galaxies
balance.
found inside large voids, including Boötes, generally align with the baseline expectations. Many are low-mass systems, many are disk-dominated, many show signs of ongoing star formation. Some are low surface
Sirius
brightness.
makes his
This is not paradoxical. Star formation can persist in isolation when gas is retained and slowly accreted, and the absence of cluster quenching processes allows even small galaxies to remain active. The sensors can therefore look surprising only if one expects void
The
galaxies
intense
to be
heat of
uniformly
Sirius
dormant
A
or
burns
absent.
at a blistering
The more meaningful question is
9,940
whether the
Kelvin.
interior contains galaxies that are unexpectedly massive or unexpectedly clustered for a deep underdensity. One potential flashpoint is the presence of a
The
relatively
life
luminous
cycle of
galaxy
Sirius A
that
mirrors
appears
that
to
of
sit
all
far from the
stars. A
boundary.
constant burn of
In a
fusion.
sparse interior, even a single luminous system draws attention, yet its significance
Sirius
depends
A
on
burns
halo mass and
brightly.
context. A luminous
quiet
galaxy can be an
existence of
outlier
Sirius
in a
B,
low-density
a
environment,
remnant
and
of its
outliers
former self,
exist.
offers a
A
contrast.
halo can be more massive than typical for its environment due to stochastic growth history. A galaxy can also be mislocated in redshift space. Peculiar velocities can move a
The dual
boundary
nature
galaxy
of the
into the
Sirius
interior
system,
in redshift
a living
space.
star and a cool.
Therefore, the census must treat such cases probabilistically and seek corroboration such as the presence of nearby faint companions that indicate a local filament or group or distance estimates beyond redshift that confirm depth. A single luminous galaxy is rarely enough to call an anomaly. A population of such galaxies or a confirmed massive group deep in the core would be more significant. Another potential flashpoint is internal structure. When the number of galaxies is small, their distribution can look lumpy. A handful of galaxies aligned in space can resemble a filament. In the baseline model, internal filaments exist. Therefore, an internal filament is not unexpected. What could be more puzzling is if the internal filament is unusually rich, with a density comparable to typical filaments outside the void, while the surrounding volume remains very empty. Such a configuration would imply a strong small-scale fluctuation embedded in a large-scale underdensity. This is possible but rare. To evaluate it, one must check completeness and ensure that the filament is not simply the part of the void where the survey is deepest. One must also check whether the filament connects to the boundary through a low-density corridor, which would make it a boundary intrusion rather than a truly isolated
Despite its
internal
brilliance,
structure.
Sirius
With deeper
light
surveys,
travels across
internal
vast
filaments can be
void.
traced more reliably, and their richness can be compared to mock catalogues. A third flashpoint involves the faint end of the census. If deep imaging reveals a large number of faint dwarfs inside the void, it can alter the narrative. It can dissolve claims of extreme emptiness while creating a different question. Why does the void host many faint galaxies, yet so few
Sirius
brighter
A's fusion
systems?
creates immense amounts
The
of energy,
baseline answer is
radiating
halo mass
light and heat
function
across the
shifting and
cosmos,
star
shaping
formation
the galaxy
suppression
around it.
thresholds. Yet the details are model sensitive. If the observed faint galaxy abundance is higher than predicted by galaxy formation models, it can indicate that models over-suppress star formation in void halos. If it is lower, it can indicate that models under-predict suppression or over-predict gas retention. Either way, the census becomes a test of halo occupation and feedback modeling. This is where genuine scientific confusion can arise because baryonic prescriptions are uncertain
Ancient cultures saw
and can
Sirius as
yield
a
different
guide,
predictions,
its position
especially in
marking the rhythms
underdense
of life,
regimes.
weather,
A
and
fourth
time itself.
flashpoint is gas-rich galaxies found in radio
Though Sirius
surveys.
B is
These
invisible
systems
to the
can be
naked
optically
eye,
faint
it
yet contain
shapes the system's
significant
balance.
neutral hydrogen. Their presence supports the baseline expectation that void galaxies can retain gas. However, the distribution and typical gas fractions matter. If Boötes contains an unusually high fraction of extremely gas-rich dwarfs, compared to models, it suggests differences in gas accretion or feedback. If such galaxies are absent, it suggests stronger suppression of baryon capture. In either case, the census becomes a multi-tracer inventory, rather than a simple optical count, and the interpretation
The
shifts from
intense heat of
emptiness to
Sirius
baryon
A
physics.
burns at a
The
blistering
claim of a hidden anomaly can also hinge on the
9,940
properties
Kelvin.
of void galaxies compared to expectations. If void galaxies show unexpectedly high star formation rates for their mass, one might infer that gas cooling and
The
molecular
life
formation
cycle of
are
Sirius
more
A
efficient
mirrors
in
that of
void
all
conditions.
stars. A constant
If they
burn
show
of fusion.
extremely low metallicities, one might infer persistent inflow of low metallicity
as
gas
Sirius
or unusually
A
slow
burns
enrichment.
brightly.
If they show unusual
The quiet
kinematics, one
existence
might
of
infer
Sirius
differences
B,
in halo
a
structure.
remnant of its former
These are
self,
plausible
offers
and
a
interesting.
contrast.
But because measurements have uncertainties, the census must be built with consistent methods. Metallicity calibrations vary. Star formation rate tracers respond
The
on
dual
different
nature of the
timescales
Sirius system,
and are
a
affected
living
differently
star
by
and a
dust.
cool.
Gas masses depend on distance. A robust anomaly claim would require a population-level difference relative to matched control samples and a comparison to simulation-based mock catalogues. In the calm view, the Boötes interior census is a sparse evolving list, whose main stable feature is low density and luminous tracers with a population of low-mass, often gas-rich galaxies embedded in weak internal structure. The most credible place for a hidden anomaly is not the mere existence of some galaxies, but the quantitative mismatch between observed abundances and model predictions for halo occupation and gas content, or a systematic pattern in properties that models fail to reproduce. Establishing that requires moving from counts to processes, beginning with how star formation proceeds in isolation, and what that implies for the observable appearance of void galaxies. The next inward step is therefore to examine star formation regulation inside the void as it relates to potential anomalies in activity, gas retention, and chemical evolution. Star formation in void galaxies is often the source of claims that something does not fit expectations, because the intuitive picture of a void suggests inactivity, while the physical baseline allows continued star formation under isolation. The next inward region is
Despite
therefore
its
the
brilliance,
regulation of star
Sirius
formation
light
inside the
travels across
Boötes
vast
void, and the specific ways that regulation can produce patterns that look anomalous when compared to models. In standard thinking, void galaxies sit in low-mass halos, accrete gas slowly, and convert it into stars with low efficiency. They can remain blue and gas-rich because external quenching is weak. Yet the details of how gas becomes molecular, how
Sirius A's
feedback
fusion
cycles
creates
operate,
immense
and how
amounts of
metallicity
energy,
evolves
radiating
can
light
differ
and
from
heat
what is
across the
calibrated
cosmos,
in denser
shaping the
environments.
galaxy around it.
Because models are often tuned to match galaxy populations in average environments, void galaxies can expose where those models are uncertain. The outer driver of star formation in a void galaxy is the ability of its halo to acquire and keep gas. The intergalactic medium is largely ionized and warm due to ultraviolet radiation. This creates a pressure barrier for low-mass halos. If a halo is too small, it cannot accrete or retain gas effectively. If it is just above the threshold,
Ancient
it
cultures
can
saw
acquire
Sirius
gas
as a
and
guide,
form a small
its
galaxy.
position marking the rhythms
This
of
creates a
life,
sensitive
weather, and
dependence
time
on
itself.
halo mass in the low-mass regime.
Though
In a
Sirius
void
B
where
is
halos are
invisible to
typically
the
low
naked
mass,
eye,
small
shapes the
differences in
system's
halo
balance.
growth histories can lead to large differences in whether a galaxy forms and how luminous it becomes. This can make the observed population seem irregular. Some halos host visible galaxies while others appear dark. Such irregularity is not necessarily anomalous, but it can become a modelling challenge if the observed fraction of luminous halos differs from predictions. Once gas is captured, it must cool to form stars. Cooling is easier in denser gas and when heavy elements are present. Heavy elements provide additional radiative
The
pathways.
intense heat of
In
Sirius
void
A
galaxies,
burns at a
metallicities
blistering
can be low, slow, and cooling.
9,940 Kelvin.
Moreover, forming the cold molecular phase depends on dust and shielding. Molecular hydrogen forms efficiently on dust grains and survives when shielded from ultraviolet
The life
radiation.
cycle of Sirius A
In low
mirrors that of all
metallicity
stars.
environments,
A
dust
constant
is
burn of
scarce
fusion.
and shielding is weaker. This means a galaxy can have a large reservoir
As
of atomic
Sirius A
hydrogen
burns
while
brightly,
forming stars slowly because the
quiet
molecular
existence
fraction
of
is small.
Sirius B,
This
a remnant
produces a
of its former
specific
self,
observational
offers a
pattern,
contrast.
high neutral hydrogen mass relative to stellar mass modest star formation rates, and extended low-intensity star formation across a diffuse disk.
The
If
dual
models
nature
assume
of the
molecular
Sirius
formation
system,
efficiency
a
is
living
calibrated
star
in
and a
higher
cool.
metallicity systems, they may overpredict star formation in void dwarfs, or mispredict the spatial distribution of star formation. A mismatch here can be framed as an anomaly, but it is a mismatch in baryonic subgrid physics rather than a contradiction in the cosmological mass field. Feedback is the next key regulator. In low-mass galaxies, supernova explosions and stellar winds can drive gas outflows. Because the gravitational potential is shallow, a given amount of energy can remove a larger fraction of gas. This can suppress star formation and create bursty histories. A galaxy forms stars in a burst, feedback heats and expels gas star formation, declines, gas cools and reaccretes, then another burst occurs. In dense environments, external gas supply and interactions can complicate this cycle. In voids where external perturbations are rare and where the gas supply can be smoother, the burst cycle can be more purely internal. This can produce galaxies whose star formation rates fluctuate strongly over time. Observationally, depending on the tracer used, a galaxy can look unexpectedly active or unexpectedly quiet. Ultraviolet emission reflects star formation over tens of millions of years. Emission lines reflect very recent massive star formation.
Despite
A
its
bursty
brilliance,
galaxy can show strong
Sirius
emission
light
lines during a
travels across
burst and
vast
weak
void.
lines soon after, even if its long-term average is moderate. Therefore, an apparent anomaly in star formation activity can sometimes be a snapshot of burst timing rather than a fundamental departure. Gas accretion in voids is another area of uncertainty. Even in under-dense regions, gas accretion continues. It may occur along faint internal filaments, or as more
Sirius
isotropic
A's
inflow
fusion
from the
creates immense
intergalactic
amounts
medium.
of energy,
The
radiating
inflowing
light and heat
gas can
across
be
the
relatively
cosmos,
low in
shaping the
metallicity.
galaxy around it.
If accretion is more effective than models assume void, galaxies could maintain higher gas fractions and sustain star formation longer. If accretion is less effective, galaxies could exhaust or expel gas and become faint. Observationally measuring accretion directly is difficult. Instead, one infers it from gas fractions, star formation histories, and metallicity patterns. A signature of ongoing low metallicity inflow is a metallicity that is lower than expected for a
cultures
given
saw
stellar
Sirius
mass
as a
combined
guide,
with high gas
its position
content.
marking the rhythms of
Another
life,
signature
weather,
is
and
extended
time itself.
outer disk star formation, where gas has
Though
recently
Sirius
settled.
B is invisible
These
to the naked
features can be
eye,
interpreted
it
within
shapes the
standard
system's
physics,
balance.
but can challenge models quantitatively. Chemical evolution provides another potential anomaly avenue. In isolation, a galaxy's metals are produced by its own stars. Some metals are retained and mixed into the interstellar medium. Some are lost in outflows. In low-mass systems, outflows can remove a significant fraction of metals. In addition, inflow of low metallicity gas can dilute the metal content. Therefore, void galaxies can have low metallicities and can show strong scatter at fixed
The intense
mass.
heat of Sirius
If the
A
scatter is
burns at a
larger than
blistering
models predict, or if
9,940
extreme low
Kelvin.
metallicity systems are more common, it suggests that models underestimate outflow efficiency, overestimate mixing, or misrepresent inflow rates. Again,
The
this
life
is an
cycle of Sirius
astrophysical
A
modelling
mirrors that of
mismatch,
all
not
stars.
necessarily a
A constant
cosmological
burn
one.
of fusion.
The absence of environmental quenching is also important. In clusters and groups,
As
galaxies can be
Sirius A
stripped of
burns
gas,
brightly,
or have their gas supply cut off, leading
the
to
quiet
quenching.
existence of
In
Sirius
voids,
B,
these
a
processes are
remnant
weak.
of its former self,
Therefore, void
offers a
galaxies can
contrast.
remain star-forming at late times. If one compares them to galaxies in denser environments without matching for mass and selection, they can seem unexpectedly active. The correct comparison
The dual
matches stellar
nature of the
mass
Sirius
and
system,
uses control
a living
samples.
star and a cool
Under matched comparisons, the expected difference is that void galaxies have higher specific star formation rates on average. If Boötes void galaxies show the opposite, such as being unusually quenched, that would be more surprising and would require explanation, possibly involving internal feedback or the ultraviolet background. A hidden anomaly framed as confusion among scientists could therefore be a disagreement about whether void galaxies in Boötes are too active, too gas-rich, too metal-poor or too bursty, relative to model predictions. The path to clarity is to measure these properties with consistent methods and compare them to matched simulation-based predictions. The most decisive combination is stellar mass-neutral hydrogen mass star formation rate and metallicity, measured for a well-defined void core sample and a matched exterior sample. This reveals whether the relationship between gas and star formation in voids matches standard prescriptions. With star formation regulation established as a likely locus of quantitative mismatch, the next inward step is to step back from galaxies into the diffuse gas of the void itself, because that gas sets the inflow reservoir and carries the imprint of enrichment and ionization. Absorption measurements of the intergalactic medium can be framed as anomalies if they show unexpectedly dense or enriched gas, and these measurements connect directly to how void galaxies exchange matter with their surroundings. The diffuse gas of the Boötes void is the largest component by volume, and the quiet background against which galaxies form and evolve. It is also the component most likely to generate a hidden anomaly narrative, because it is hard to observe and easy to misinterpret when only a few measurements exist. The next inward region is therefore the absorption tests that probe void gas and the specific patterns that would justify genuine confusion if they persist under careful analysis. In the baseline picture, void gas is low density and highly ionized, making absorption weaker on average than in filaments. Metals are present at lower average abundance, so metal lines are rarer and weaker. Yet internal filaments and halo outskirts can produce stronger absorption locally. Therefore, a single strong absorber is not necessarily anomalous. The anomaly would be a systematic pattern such as core sight lines showing absorber strengths and metallicities similar to boundary or filament environments,
its
or
position
core sight
marking the
lines
rhythms
showing
of life,
unexpectedly
weather,
frequent
and time
metal-enriched
itself.
systems without nearby galaxies.
Though
Absorption
Sirius
measurements
B
begin
is
with
invisible
background
to the
sources,
naked
typically
eye,
quasars.
It shapes the
The
system's
quasar
balance.
spectrum contains light that has passed through intergalactic gas along the line of sight. Hydrogen produces the Lyman alpha absorption line when neutral, and a forest of such lines can appear at different redshifts corresponding to different gas clouds along the path. In the low redshift universe relevant for Boötes, the absorption forest is sparser than at high redshift, but individual absorbers can be studied in detail. The strength of a hydrogen absorber depends on the column density of neutral hydrogen.
The
Column
intense heat
density
of
is the
Sirius
integrated
A
number of
burns at a
atoms
blistering
along the line of sight.
9,940
In
Kelvin.
photoionized gas, the neutral fraction depends on density and on the ultraviolet background. In low-density void gas, the neutral fraction is small, so even a
The life
substantial
cycle of
total gas
Sirius A
column can
mirrors
yield
that of
weak
all
neutral
stars,
absorption.
a constant burn of
This
fusion.
means that interpreting hydrogen absorption requires ionization modeling.
As Sirius
A weak
A
absorber does not
burns
necessarily
brightly,
mean little gas. It can mean
the
highly
quiet
ionized
existence of
gas.
Sirius
A
B,
strong absorber
a
can mean a
remnant of its
denser
former
region,
self,
but it can also
offers a
arise from a
contrast.
small dense cloud associated with a halo or a galaxy. Metal absorption lines such as those of carbon and oxygen ions provide clues about enrichment. Metals
The dual
originate in
nature of the
stars and are
Sirius
dispersed
system,
by winds
a
and
living star
outflows.
and a cool.
In a void, fewer galaxies imply less enrichment on average. Therefore, metal absorbers are expected to be less common. If metal lines are found in the void core, there are several conventional possibilities. The absorber could be associated with a faint dwarf galaxy below detection limits. It could be associated with a low-mass halo hosting little starlight. It could lie in an internal filament where gas density is higher and where a small number of galaxies have enriched their surroundings. It could also reflect long-range transport of metals from boundary galaxies through winds over long times. Such transport is possible because low-density environments offer less resistance, but its efficiency and reach are uncertain. A persistent pattern of metal enrichment in the deep core, especially if no galaxies are found nearby down to deep limits, could therefore be a meaningful tension with some models. The tension would be with enrichment and transport physics rather than with the existence of the void. The geometry of absorption sampling is a major constraint. A void covers a large sky area. The number of suitable quasars behind it may be small. Each quasar provides a pencil beam. Therefore, measurements can be dominated by chance intersections with internal filaments. In simulations, even deep void interiors contain occasional higher density structures. The probability that a random sightline intersects such a structure is low but not zero. With only a few sightlines, one can easily pick up an unrepresentative sample. This is why robust void gas results often come from stacking many voids and many sightlines. For Boötes, a careful approach treats existing absorption detections as suggestive rather than definitive unless the sightline sampling is dense. Confusion can arise when a small number of detections are treated as representative of the entire void. Ionization modeling is another source of ambiguity. The ultraviolet background intensity and spectrum at low redshift are not perfectly known. Small changes in assumed background can change derived densities and metallicities. Temperature also matters. Some absorbers can be in a warmer phase, and collisional ionization can contribute. Without multiple ions to constrain conditions, derived metallicities can have large uncertainties. Therefore, a claim that void gas is unexpectedly enriched must show that the enrichment is not an artifact of assumed ionization conditions. This usually requires detecting multiple ionization stages of the same element or multiple elements, and fitting a model that constrains density and ionization parameter. Without this, enrichment estimates can be uncertain. Associations between absorbers and galaxies are also uncertain. To determine whether an absorber is truly intergalactic void gas, or the extended halo of a galaxy, one must search for galaxies near the absorber's redshift and impact parameter. In voids, the nearest galaxy can be far. Yet faint galaxies can be missed. Deep imaging and spectroscopy around the sightline are needed to rule out hidden associations. If no galaxies are found within a large radius down to deep limits, an absorber may be genuinely intergalactic. In that case, its metallicity and density become more informative about enrichment reach. A pattern of metal-enriched absorbers with no galaxy associations in the void core would be more surprising than metal absorbers near known galaxies. Hydrogen absorption can also reveal a different kind of anomaly, the absence of expected absorption. If models predict a certain frequency of weak absorbers in void cores based on baryon density and ionization, and observations find significantly fewer, it could suggest that baryons are distributed differently, or that the gas is more highly ionized or hotter than expected. Because void gas is hard to detect in emission absorption, is one of the few ways to test baryon content. A systematic deficit of absorbers could be framed as missing baryons in voids. However, the interpretation is sensitive to selection in quasar sightlines and to detection limits in spectra. A weak absorber can be missed in noisy data. Therefore, careful completeness modeling of absorber detection is required. A hidden anomaly narrative could therefore arise from a claim like this: the Boötes core shows unexpectedly strong and frequent metal absorption, implying enriched gas where there should be little, or it shows unexpectedly little absorption, implying an even emptier baryon content than expected. Both claims are plausible to test, but require multiple sightlines and rigorous modeling. If supported, they would not necessarily overturn the cosmological framework, but they could challenge models of how gas is heated, ionized and enriched in low-density environments. With the diffuse gas layer examined, the next inward step is to return to the invisible mass layer, the dark matter, and to separate what is truly a mass anomaly from what is a light and tracer anomaly. This involves the relationship between halo populations and observed galaxies, and the use of gravitational and dynamical probes to infer whether the void's mass deficit is extreme enough to warrant the word anomaly in the cosmological sense. The most important distinction in any void anomaly claim is the distinction between a void in light and a void in mass. The next inward region is therefore the relationship between dark matter structure and observable traces inside the Boötes void, and the limited but meaningful ways to test whether the void's mass deficit is truly extreme. In the standard model, dark matter dominates the mass budget and forms the gravitational scaffolding. Galaxies form in dark matter
Sirius A's fusion
halos,
creates
but
immense
not in
amounts of
all
energy,
halos,
radiating
and
light
not
and
with
heat across the
uniform
cosmos,
efficiency.
shaping the
In
galaxy
under
around it.
dense environments, halo growth is slowed, and high mass halos are rare. This makes bright galaxies rare. The result is that a void can look dramatically empty in a bright galaxy map, while the mass field remains only moderately underdense. Many supposed void anomalies dissolve when this mapping is handled correctly, because the model prediction for luminous tracers already anticipates a deep deficit. Halo population predictions inside voids are one of the clearest baseline statements.
Ancient
Simulations
cultures saw
predict that the
Sirius as a
halo
guide,
mass function
its
inside a
position
void
marking
is
the
shifted
rhythms of
toward low
life,
masses.
weather, and time
The number
itself.
of halos above a high mass threshold drops strongly.
Though Sirius
This
B
alone
is
can
invisible
explain
to the
why
naked
luminous
eye,
galaxies are
it shapes
scarce.
the system's
Low mass
balance.
halos remain, but many of them may host galaxies too faint to detect, or may host no stars at all. This creates a population of dark halos. Their existence is not directly observed, but it is consistent with the overall success of the model in explaining galaxy clustering, and with the need for suppressed star formation in low-mass halos after reionization. In the Boötes interior, therefore, the baseline is that there can be many gravitational structures that are invisible in
The
optical
intense
surveys.
heat of Sirius A
This is why the
burns at a
phrase
blistering
hidden anomaly must be treated
9,940
carefully.
Kelvin.
Hidden structure is expected. The anomaly would be hidden structure that is too massive or too abundant relative to predictions. The first direct route to mass information
The
is
life
weak
cycle of
gravitational
Sirius A
lensing.
mirrors that of
A
all
mass
stars.
deficit in a void
constant
produces
burn
a
of
subtle
fusion.
lensing signature, a systematic distortion of background galaxy shapes.
As
In
Sirius
principle,
A burns
this provides a
brightly,
tracer-independent measure of the
the
projected
quiet
mass
existence
profile.
of Sirius
In
B,
practice, the
a
signal
remnant
from a
of its
single
former
void is
self,
small.
offers a
Noise from the
contrast.
intrinsic shapes of background galaxies is large. Systematic errors in shape measurement can be comparable to the expected signal. Therefore, most robust lensing void results come from
The dual
stacking many
nature of the
voids.
Sirius system,
For Boötes,
a living
lensing can
star
still
and
be
a
useful
cool-
as a consistency check if wide-area, high-quality shear catalogues are available, and if the void is large enough that the signal integrated over its area can be extracted. The key point is conceptual. If lensing indicates only a moderate mass deficit, then the void's dramatic emptiness in luminous galaxies is explained by bias and halo occupation. If lensing indicates an unusually deep deficit for a void of its size, the case for a cosmological anomaly strengthens. Without lensing, mass claims remain indirect. The second route is dynamics. The void's mass deficit produces an outflow velocity field. Galaxies near the void boundary and just outside should show redshift space distortion patterns consistent with this outflow. By modelling the anisotropy of galaxy distributions around the void, one can infer a combination of density profile and velocity profile, which constrains the gravitational potential. This method depends on tracer bias and on redshift errors, but it is often more accessible than lensing for a single prominent void because it uses the same galaxy survey that defines the void. For Boötes, the sparse interior means the dynamic information comes mainly from the boundary region. The resulting inference is therefore about the overall mass deficit and compensation, not about detailed core structure. A dynamic
Despite its
result
brilliance,
consistent with moderate
Sirius
mass
light
deficit
travels across
supports the
vast void.
baseline. A result demanding a very deep deficit could motivate closer scrutiny. A third route to mass information is the census of groups and clusters, because the presence of a rich cluster deep in the void core would imply a massive halo. Such a presence would be difficult to reconcile with a deep underdensity unless the void definition is broad and includes regions not truly
Sirius
core.
A's fusion creates immense
Therefore,
amounts
if
of
a
energy,
claim of anomaly
radiating
involves a
light and
massive
heat
group
across the
inside
cosmos,
Boötes,
shaping
the
the
first
galaxy
step
around
is
it.
to examine whether the group is truly isolated in low-density surroundings, or whether it sits on a boundary filament. Group richness, galaxy velocity dispersion, and X-ray emission can help estimate mass. Yet even here, selection effects matter. groups are easier to detect when their member galaxies are bright. In voids, groups may be missed. Therefore, the absence of groups does not strongly constrain mass, but the presence of a clearly massive group in the core would be a strong data point that requires careful
Ancient
membership
cultures saw
verification.
Sirius as a guide,
Halo,
its position
occupation.
marking the rhythms of
The mapping
life,
from halos
weather,
to
and
galaxies
time
is where
itself.
many model uncertainties concentrate.
Though Sirius
Semi-analytic
B
models
is
and
invisible to the naked
hydrodynamic
eye,
simulations make
it
different
shapes the
predictions
system's balance.
for how many low-mass halos host detectable galaxies and how luminous those galaxies are. In voids, where the halo mass distribution is shifted downward, these differences can translate into large differences in predicted galaxy counts. Therefore, an apparent mismatch between observed and predicted void galaxy counts can reflect differences in halo occupation modelling rather than new cosmology. This is especially true when the tracer threshold is near the faint end where completeness is uncertain. A true cosmological
heat of
anomaly would
Sirius A
require that the
burns at a
mass under
blistering
density itself is inconsistent,
9,940
not simply
Kelvin.
the galaxy occupation. This leads to a practical definition of what would count as a cosmological anomaly in Boötes. It would be a combination of void size and mass depth
The
that is
life
too
cycle of
improbable
Sirius
under the
A
standard
mirrors that
initial
of all
condition
stars, a
statistics,
constant
given
burn
the
of
survey
fusion.
volume confirmed through mass-sensitive probes and robust void definition. It would likely also be accompanied by unusual dynamics consistent with the
The
deeper
quiet
mass
existence of
deficit.
Sirius B,
It would not be
a remnant
established
of
by
its
a
former
bright
self,
galaxy emptiness
offers a
map alone.
contrast.
By contrast, what would count as a galaxy formation anomaly would be a mismatch in the occupational properties of low-mass halos in voids, such as too many or too few
The
dwarves,
dual nature
or a
of the Sirius
systematic
system,
offset in
a
star
living
formation
star and a
efficiency and
cool
metallicity patterns compared to model predictions. These are meaningful anomalies, but they are in baryonic modelling. The phrase scientists confused often reflects this layering. One group might emphasise that the void's galaxy emptiness looks too extreme compared to a naive expectation, and might suggest new physics. Another group might note that when bias and selection are included, the mass field remains consistent and the apparent extremeness is expected. The resolution is to compare to mocks with matched selection, and to use mass probes where possible. Confusion persists when these steps are not available or when data are insufficient. With the dark matter and tracer relationship established, the next inward step is to examine the void's dynamics and redshift space distortions more explicitly, because these are the most accessible mass-related signals for a void defined in galaxy surveys. Dynamics can provide a bridge from the void's galaxy-defined profile to its inferred mass profile, and any inconsistency there is a more meaningful candidate for a hidden anomaly than a dramatic-sounding galaxy count alone. Dynamics is the quiet language of mass, and in a void it appears as a coherent outflow pattern that can be detected indirectly through redshift space distortions. The next inward region is therefore the dynamic signature expected around the Boötes void, and the
Despite its
specific
brilliance,
ways in which a dynamic
Sirius
measurement
light
could either
travels
support
across
the
vast
baseline
void.
picture or motivate genuine confusion. The baseline expectation is that the underdensity produces an outward peculiar velocity. Field galaxies and matter move away from the void center relative to the average expansion. This motion is not a separate expansion of the void. It is the result of gravity acting on a density gradient in an expanding
Sirius A's
universe.
fusion creates immense
Because
amounts of
galaxy
energy,
redshifts
radiating
combine
light and heat
expansion
across
and
the
peculiar
cosmos,
motion,
shaping the
the
galaxy
outflow
around
leaves
it.
an imprint on the apparent shape and density profile of the void in redshift space. The key quantity is peculiar velocity along the line of sight. In redshift space, a galaxy's inferred distance is shifted by its line of sight velocity component. If a galaxy on the near side of the void has a peculiar velocity toward the observer, its redshift is reduced, and it appears slightly closer than it would in pure expansion. If a galaxy on the far side has a peculiar velocity away from the observer,
Ancient
its
cultures saw
redshift is
Sirius as a
increased,
guide,
and it
its
appears
position
slightly
marking the
farther.
rhythms of life,
The
weather,
collective
and time
effect can
itself.
stretch the void along the line of sight depending
Though
on
Sirius
geometry.
B is
The
invisible to
effect
the
can
naked
also
eye,
compress features
shapes the
depending on how
system's
velocity
balance.
gradients vary with radius. the observable is an anisotropy in the distribution of galaxies around the void, the pattern looks different along the line of sight than across the sky. In practice, one measures this anisotropy statistically. A common approach is to compute the void galaxy cross-correlation function, describing how galaxy density varies with distance from void centers, separated into components parallel and perpendicular to the line of sight. If the void were observed in real space without
The
velocity
intense heat of
distortions,
Sirius A
the profile
burns at a
would be
blistering
isotropic around the center when
9,940
averaged
Kelvin.
over many voids. In redshift space, anisotropy appears due to velocities. The model predicts a relationship between the density profile and the velocity
The
profile.
life cycle of Sirius
In linear
A
theory
mirrors
and
that
its
of all
extensions,
stars.
the velocity
constant
field is
burn
linked
of
to the
fusion.
enclosed mass deficit. Therefore, by fitting the anisotropic correlation function, one can infer the velocity profile and thereby constrain the mass profile and the growth rate of structure.
its former self.
For an
offers a
ensemble of
contrast.
voids, this method can test cosmological parameters. For a single void like Boötes, the statistical power is lower, but the method still offers a consistency check. A major limitation for Boötes is tracer sparsity in the interior.
A living
The
star and a
anisotropy
cool
signal is dominated by galaxies near the boundary and in the surrounding regions, because that is where the density of tracers is higher. This means the dynamic inference is more sensitive to the void's outer profile and compensation than to the deep core. If the void has a compensating ridge, the ridge's mass can alter velocities near the boundary, potentially producing a characteristic change in the anisotropy pattern. If the void is uncompensated, the outflow pattern can extend to larger radii. Therefore, measuring how the anisotropy changes with radius can distinguish compensated from uncompensated profiles. For Boötes, this would require a dense enough surrounding sample to measure the profile with reasonable precision, and it would require careful control of survey selection. Another limitation is redshift error. Even small redshift uncertainties translate into distance uncertainties along the line of sight. In void analyses, this smears the density field and reduces anisotropy. If redshift errors vary across the survey, the effect can mimic or obscure dynamical signals. Modern spectroscopic redshifts are precise, but if the void census includes heterogeneous redshifts from different instruments or includes photometric redshifts, uncertainties can be larger. Therefore, a robust
Despite its
dynamic
brilliance,
analysis uses a
Sirius light
homogeneous
travels
spectroscopic
vast
sample
void.
and models redshift errors explicitly. Without this, a mismatch between observed and predicted anisotropy could be a measurement artifact rather than an anomaly. Tracer bias is another complication. Galaxies are biased tracers of mass, and bias can vary with environment and galaxy type. In voids, the galaxies that are detected may represent a special subset,
Sirius A's
such as
fusion
higher
creates
surface
immense
brightness
amounts of
systems,
energy,
or
radiating
systems
light
with
and
certain
heat across
star
the
formation
cosmos,
properties.
shaping the galaxy
Their
around it.
spatial distribution relative to mass can differ from the distribution of the underlying mass. If a model assumes a certain bias relation and the real bias differs, predicted anisotropy can mismatch observed anisotropy. This could be framed as a confusion if interpreted as a failure of gravity, when it's actually a failure of tracer modelling. The remedy is to use mock catalogues that include the same selection, and to calibrate bias using clustering measurements in the same data. The most meaningful
Ancient
candidate
cultures
for a
saw
hidden
Sirius as a
anomaly in
guide,
dynamics
its
would
position
be a
marking the
persistent
rhythms of life,
inconsistency
weather,
between the
and
void's
time
observed
itself.
density profile and its inferred
Though
velocity
Sirius B
field
is
under
invisible to the
standard
naked
gravity
eye,
after
it
tracer
shapes the
bias
system's
and
balance.
redshift errors are accounted for. For example, if the galaxy profile suggests a certain mass deficit under a reasonable bias model, but the anisotropy implies a velocity field too strong to be produced by that deficit, it would suggest either that the mass deficit is deeper than inferred from galaxy density, or that the growth rate of structure differs. Conversely, if the anisotropy implies a much weaker velocity field than expected, it could suggest a shallower mass deficit or a different bias relation.
The
In either
intense
case,
heat
the
of
next step
Sirius
would be
A
to seek
burns
an
at a
independent
blistering
mass probe such as lensing.
9,940 Kelvin.
Without lensing, dynamics alone cannot uniquely determine whether the mismatch is in mass growth or bias. The local environment around Boötes also matters. The void's velocity field
The
is not
life
purely
cycle of
radial
Sirius
and not
A
purely
mirrors that
symmetric.
of all stars.
Nearby
A constant burn
overdensities
of
exert
fusion.
tidal influences that can distort flows. This can produce directional differences in outflow strength. For a single void, these anisotropies can be large and can confuse simple spherical models. Therefore, a careful analysis either restricts itself to statistical averages in large samples or uses simulations to model the specific environment. For Boötes, the practical approach is to construct constrained simulations
The dual
or
nature
to
of the
select
Sirius
analog
system,
voids in
a living
simulations
star
with
and a
similar
cool-
environment and then compare. Without this, deviations from simple models can be misread as anomalies when they are actually consequences of irregular geometry. Even with these limitations, dynamics remains valuable because it tests the underlying gravitational picture in a way that galaxy counts alone do not. A void that looks extreme in bright galaxy maps could still have modest dynamics if the mass deficit is moderate. Conversely, strong dynamics would indicate a deeper mass deficit. Therefore, dynamics can either support the baseline interpretation that the void is an extreme tracer feature, or motivate deeper investigation if the inferred mass deficit appears unusually large. Having established dynamics as a bridge from tracer-defined voids to mass inferences, the next inward step is to examine the systematics that most commonly mimic dynamic anomalies, including survey geometry, boundary definition effects, and shot noise. These systematics can produce apparent anisotropies and apparent inconsistencies. Before any dynamic discrepancy can be called an anomaly, it must survive these stress tests, especially in a sparse region where statistical fluctuations can be large. A dynamic anomaly in a void is easy to imagine and hard to establish because redshift space distortions are subtle, and because the measurement depends on how the survey samples space. The next inward region is therefore the specific set of systematics that can mimic or distort the dynamic signature around the Boötes void, producing apparent inconsistencies that could be mistaken for a hidden anomaly. These systematics overlap with general void systematics, but here they are framed specifically through their effect on anisotropy and inferred velocity fields. The aim is to identify how an apparent mismatch between
Sirius A's
density
fusion
profile and
creates immense
velocity
amounts of
profile
energy,
can arise
radiating
without
light and
any
heat
new
across the
physics,
cosmos,
and how one would
shaping the
recognize
galaxy
and
around it.
control these effects. Survey geometry is the first and most basic systematic. A void covers a large sky area. If the survey footprint truncates part of that area, the measured density profile becomes anisotropic, even in real space, because one direction is missing data. When anisotropy is then interpreted as a redshift space distortion, a false velocity signal can be inferred. The standard mitigation is to use random catalogues that replicate the survey footprint in selection
Ancient cultures
and to
saw Sirius
normalize
as a
densities
guide,
accordingly.
its position marking the
But in
rhythms
void
of life,
analyses, the
weather,
footprint
and
can
time
still
itself.
matter, because void finding itself can be biased near survey edges. A void can be artificially extended into unobserved regions. Then the inferred center shifts, and the anisotropy measurement becomes contaminated. For Boötes, any dynamic analysis must demonstrate that the void center and boundary are stable when restricting to well-observed regions, and that the anisotropy signal is not dominated by the direction of a survey edge. Radial selection and redshift-dependent completeness are the second systematic. Galaxy surveys have a selection function. The number of galaxies detected per unit volume
The intense
decreases
heat of
with
Sirius
distance
A burns
because
at a
faint
blistering
galaxies fall below the magnitude limit.
9,940 Kelvin.
Void analyses often circumvent this by using volume-limited samples, but volume limitation reduces tracer density and increases shot noise. If a
The life cycle of
flux-limited
Sirius
sample
A
is used
mirrors
with
that of all
weights errors
stars.
in the
A
selection
constant burn
function
of
can
fusion.
create artificial radial density gradients. These gradients can align with the line of sight and mimic anisotropy. Even in volume-limited
quiet
samples,
existence of
spectroscopic
Sirius
completeness
B,
can
a
vary with
remnant
sky
of its
position
former self,
and can
offers a
correlate with observing
contrast.
conditions. If completeness varies with redshift due to instrumental effects, it can create line-of-sight patterns. Therefore, a robust anisotropy measurement requires either a
The
volume-limited
dual
sample
nature of the
with
Sirius
well-characterized
system,
completeness,
a living star
or a
and
carefully
a cool
validated selection function in a weighted sample. Redshift errors are the third systematic. Even small uncertainties in redshift translate into uncertainties in line-of-sight position. This smearing reduces the contrast of void boundaries and suppresses anisotropy because the directional signal is blurred. If redshift errors differ between galaxy types, such as between emission line galaxies and absorption line galaxies, then the tracer population used in the analysis can have type-dependent smearing. In void interiors, the tracer population may be biased towards certain types, such as star-forming dwarfs with emission lines. In boundary regions, the population may be different. If the analysis mixes these types without modelling their redshift errors, the inferred velocity profile can be biased. This can produce an apparent inconsistency between density and velocity. The mitigation is to use homogeneous redshift measurements and to include redshift error convolution in the model fitting. Void center definition is the fourth systematic, and it is subtle but critical. Anisotropy measurements are sensitive to how void centers are defined. If the center is defined as the center of a maximal empty sphere, it targets the emptiest core. If it is defined as the volume-weighted centroid of a watershed basin, it can be offset toward regions with complex boundary shapes. If centers are biased systematically along the line of sight due to redshift space distortions, the resulting anisotropy can be misestimated. For Boötes, where the void may be a merged structure with subbasins, the choice of center can change the measured profile. A mismatch between observed and predicted anisotropy can arise simply because the model assumes spherical symmetry
Sirius
around a
A's
center
fusion creates
that
immense
does not
amounts of
correspond
energy,
to the dynamical
radiating light
center
and
of the
heat
mass
across the
deficit.
cosmos, shaping the
Therefore,
galaxy
one
around
must
it.
test center definitions and show that results are stable across reasonable choices. Boundary definition is the fifth systematic. The void boundary region is where most tracers lie and where the velocity field transitions. If the boundary is misestimated, the inferred velocity profile changes. A common issue is contamination by boundary intrusions, thin filaments that extend inward. If such a filament is included as part of the void boundary, rather than recognized as an intrusion, the density
Ancient
profile can
cultures saw
appear less
Sirius
deep,
as a guide,
and the
its position
anisotropy
marking the
signal can be
rhythms of
altered.
life, weather,
Similarly,
and
if
time
the void is
itself.
defined too broadly and includes
Though
regions that are
Sirius
not truly
B
underdense,
is
the
invisible to the
density
naked
profile
eye,
becomes
it shapes
shallower,
the
and
system's
the
balance.
expected velocity field becomes weaker. The observed anisotropy might then appear too strong, creating a false anomaly. The mitigation is to use local density criteria and to compare to mocks that include the same void-finding procedure. Shot noise is the sixth systematic and is especially severe for Boötes. With few galaxies in the interior, the measured density profile is noisy. Noise in the profile propagates to noise in predicted velocities if one uses the profile to infer mass deficit.
The intense heat
In addition,
of Sirius
noise
A
in the
burns at
positions
a
of boundary
blistering
galaxies can create random
9,940
anisotropies
Kelvin.
in the cross-correlation function. When the number of tracers is small, the covariance of the measurement is large and can be non-Gaussian. If one uses a model fitting procedure that
The
assumes
life
simple
cycle of
Gaussian
Sirius
errors,
A mirrors
the
that
inferred
of all
parameters
stars.
can be
A
biased,
constant burn
and
of
apparent
fusion.
discrepancies can be overstated. The remedy is to estimate covariance
As
from mock
Sirius
catalogues
A
or jackknife
burns brightly,
resampling, and to report
The
uncertainties
quiet
accordingly.
existence of
A
Sirius
dynamic
B,
anomaly
a remnant
cannot be
of its
credible
former
without
self,
robust error
offers a
estimation.
contrast.
Environmental tides and asphericity form the seventh systematic. A real void is not spherical. The surrounding mass distribution exerts tidal forces that shape the void
The
and its
dual
velocity
nature of the
field.
Sirius system,
This can
a
produce
living star and a
anisotropic flows that differ from spherical model predictions. For an ensemble of voids, these effects average out. For a single void, they can dominate. If one fits a spherical model to a spherical void, one can infer a wrong velocity profile and interpret the mismatch as anomalous. The proper approach is either to restrict the claim to the spherical average component or to model the void in a simulation that reproduces similar environment and then compare in that context. Finally, tracer type selection can distort dynamic inferences. If one uses only a subset of galaxies such as star-forming emission line galaxies, one probes a biased subset of halos with particular velocities and environments. The density and velocity fields traced by that subset can differ from the underlying mass field. Therefore, anisotropy measured with one tracer type may not match predictions calibrated on another. For Boötes where tracer counts are already low, the choice of tracer type can shift results. A robust analysis either uses a broadly selected tracer sample or explicitly models the tracer selection using mocks. These systematics show why confusion can persist even with good intentions. A reported dynamic mismatch may be a combination of center choice boundary definition survey geometry and shot noise rather than a physical anomaly. The path to clarity is to repeat the analysis under multiple reasonable choices and to compare to mock catalogues that include the same survey selection and void finding steps. If the mismatch persists and remains statistically significant, then, and only then, does it become a candidate anomaly worthy of deeper theoretical attention. With systematics acknowledged, the next inward step is to place Boötes and any claimed anomaly within statistical context,
Sirius
cosmic
A's fusion
variance,
creates
and
immense
the
amounts
look
of energy,
elsewhere effect.
radiating light and heat
Even a
across the
perfectly
cosmos,
measured extreme
shaping the
void
galaxy
can be
around
rare
it.
and still expected. Understanding rarity properly is essential for deciding whether the word anomaly is scientifically justified, or whether the feature is simply an extreme but allowed outcome. Statistical context is the quiet filter that separates a true anomaly from a vivid but expected extreme. The next inward region is therefore the probabilistic framing of a named void, and any interior feature described as confusing, because in a universe shaped by random initial fluctuations,
Ancient
extremes
cultures saw
are not
Sirius
only
as a
possible
guide,
but
its
inevitable
position
within
marking the
large enough
rhythms of
survey
life,
volumes.
weather, and
The
time
Boötes
itself.
void is prominent partly because it is large and
Though
nearby,
Sirius B
but also
is
because it is
invisible to the
memorable
naked
and
eye,
named.
it shapes
Naming
the system's
itself
balance.
is a selection. A named object is often the most striking example in a search. This selection changes the probability question. One does not ask how likely a random void is to be that extreme. One asks how likely the most extreme void in the surveyed region is to be that extreme. Cosmic variance is the first ingredient. It describes the fact that a finite region of the universe contains a particular realization of the density field. Even if the underlying statistical model is fixed, different regions
The
can contain
intense
different
heat of
numbers of
Sirius
large
A
voids and
burns at a
clusters.
blistering
The variance is larger for
9,940
rarer
Kelvin.
objects. A very large void is a rare object. Therefore, the number and properties of such voids in a given survey can vary widely. If a survey is small,
The life
finding a
cycle of
prominent
Sirius
void
A
might be
mirrors that of
surprising.
all stars.
If a survey is
constant
large,
burn of
finding at
fusion.
least one prominent void is expected. The relevant quantity is the effective
Sirius
survey
A
volume,
burns
the
brightly.
volume in which a void of Boötes-like size could have
quiet
been
existence
found,
of Sirius
given the
B,
survey's
a
sky
remnant
coverage
of its
depth
former
and
self,
selection.
offers a
If the
contrast.
survey volume is large compared to the void volume, then a rare object can still appear with non-negligible probability. This is often the case in modern redshift surveys. The look
The dual
elsewhere
nature
effect
of
is
the
the second
Sirius
ingredient.
system, a living
When
star
one scans a
and a cool
map for unusual features, one implicitly performs many trials. Even if the probability of a particular feature at a particular location is small, the probability that a feature of comparable extremeness appears somewhere in the scanned region can be much larger. For voids, the number of effectively independent locations and scales can be large, because void finding can identify voids at many sizes and positions. Therefore, a void that seems to have very low probability under a naive calculation can become plausible once the multiple trial nature of the search is accounted for. This does not mean that probabilities are meaningless. It means they must be computed for the correct question, the extremeness of the maximum void in a survey, not the extremeness of a randomly chosen void. Tracer bias and definition dependence are the third ingredient. The distribution of void sizes and depths depends on how voids are defined and on which tracer sample is used. Bright galaxies produce larger and deeper voids than faint galaxies. Different void finders produce different catalogues. Therefore, a probability statement must specify the void definition and tracer. Model comparisons must use mock catalogues that apply the same definition to simulated data with the same selection. Without this, the probability can be misestimated. A void can appear too large if one compares a bright galaxy-defined void to a mass field void distribution. Under matched definitions, the same void may be within expected tails. Joint distributions matter as well. A void has multiple properties: effective radius, central density, ellipticity, compensation, ridge strength, and environment. These properties are correlated. A probability statement about one property alone can be
Serious
misleading.
fusion creates
A
immense
void might
amounts
be
of energy,
large, but not very
radiating
deep in
light
mass.
and heat across the
It
cosmos,
might be deep in
shaping the galaxy around
density,
it.
but shallow in mass. It might be elongated due to environment. A claim that the void is inconsistent with models often hinges on an implicit combination of properties. The correct test uses the joint distribution of properties in mocks. If the observed combination lies far into the tail of the joint distribution, even under match selection, then the case for tension strengthens. If it lies within the expected scatter, then the void is an expected extreme. Interior features are subject to the same statistical logic.
Its position
A single
marking the rhythms
unusual
of life,
galaxy inside
weather,
the void
and time
can seem
itself.
astonishing because the void interior is
Though
sparse.
Sirius
But
B
in a large
is
enough
invisible to the
universe,
naked
unusual
eye,
galaxies
it
exist
shapes the system's
everywhere,
balance.
and some will fall in void interiors by chance. The probability question must again be framed correctly, given the number of void galaxies observed and the selection applied. How often should one find a galaxy with those properties? If the selection is targeted toward unusual objects, the probability changes. If the object is chosen because it is unusual, one must account for that. Therefore, a hidden anomaly claim based on a specific object must be evaluated with a predefined search criterion
The intense
and a
heat
control
of Sirius
sample.
A burns
The same
at a blister
applies to absorption features.
9,940
A strong
Kelvin.
absorber along a void sightline can be rare, but if one looks at many sightlines across many voids, rare absorbers will occur. The probability that at
The life
least
cycle
one
of
strong
Sirius
absorber
A mirrors
appears in the
that of all
set can be
stars. A
substantial.
constant burn of
Confusion
fusion.
arises when a single absorber is treated as representative of the void's gas,
As Sirius
rather than
A
as one
burns
draw from a
brightly.
distribution. The proper
The quiet
approach measures the
existence of
distribution of
Sirius B,
absorbers across
a
many
remnant of its
sightlines,
former self,
and compares
offers
it
a
to
contrast.
simulations. For Boötes, this requires multiple sightlines, or a careful comparison to analog voids in simulations. Statistical context also includes the distinction between
The
tension
dual
with
nature of the
cosmology
Sirius
and
system,
tension with
a living
astrophysical
star and a cool.
prescriptions. Even if an observed void property is in the tail of the distribution under a particular galaxy formation model, it might not be in the tail under another plausible model. In such a case, the data constrain baryonic modeling rather than cosmological parameters. A robust cosmological anomaly would require that the void's mass distribution inferred through gravitational and dynamical probes is inconsistent across a broad class of galaxy formation models and remains implausible under reasonable cosmological parameter variations given independent constraints. This is a high bar. For most void-related claims, the more realistic outcome is that the void provides a useful constraint on galaxy bias halo occupation and gas physics in underdense environments. This statistical framing does not damp interest, it clarifies it. The Boötes void is valuable because it is extreme. Extremes test models. But extremes must be assessed as extremes, not as impossibilities. The phrase "scientists confused" becomes scientifically meaningful when it refers to a quantified mismatch that persists under matched definitions and robust statistics, rather than to a difference in intuition. With statistical context set, the next inward step is to focus on decisive measurements. The goal is not to multiply interpretations, but to identify
Despite
which
its
observations can most
Sirius
efficiently
light
distinguish
travels across
between a
vast
normal
void.
extreme, a measurement artifact, a baryonic modelling mismatch, and a genuine mass field anomaly. These measurements must be feasible and must map directly onto observables that simulations can predict under the same selection. A decisive evaluation of a hidden anomaly in the Boötes void is less about dramatic single observations and more about building a set of measurements that
Sirius
constrain
A's
each
fusion
layer of
creates
the void
immense amounts of
problem,
energy,
from tracer
radiating light
completeness
and heat
to
across
gas
the
physics
cosmos,
to
shaping
mass
the galaxy
inference.
around it.
The wind down gathers these measurements in a steady order from the easiest to define to the hardest to obtain, while staying within what can be tested without speculation. The first step is to lock the void definition to a specific tracer sample with a well-measured selection function. That means using a volume-limited galaxy sample with a clear luminosity threshold and a completeness map across the sky, then applying a void finder whose behaviour near masks and edges is validated
Ancient
on mock
cultures saw
catalogues.
Sirius as a guide,
With this,
its
the
position
void centre
marking the
boundary
rhythms
and
of
core
life,
region
weather,
become
and time
reproducible.
itself.
Any claimed anomaly can then be referenced to a stable
Sirius
interior
B is
rather than to
invisible
a shifting
the naked
outline.
eye.
The
It
second
shapes the
step is to
system's
measure how
balance.
much of the void's apparent emptiness is due to hidden low surface brightness systems. Deep imaging with detection tuned to diffuse light and a strategy for obtaining reliable redshifts for faint targets can reveal whether the core hosts a significant population of galaxies that standard pipelines miss. If the census grows substantially under such observations, then the anomaly narrative moves away from emptiness and toward the details of faint galaxy formation. If the census remains sparse, even with deep
The
low
intense
surface
heat of
brightness
Sirius A
sensitive
burns at a
data,
blistering
then the void's extremeness becomes
9,940
more robust
Kelvin.
in tracer space. The third step is to add a complementary census through neutral hydrogen surveys, because gas-rich galaxies can be optically faint. Mapping
The life
neutral
cycle of
hydrogen in
Sirius
and across
A
the
mirrors
void
that of all
can
stars.
test whether low-mass
A constant
halos
burn
retain
of
cold
fusion.
gas as expected, and whether gas-rich systems cluster along internal
As
filaments.
Sirius A burns
Gas masses
brightly,
combined with stellar masses
the
constrain gas
quiet
fractions,
existence of Sirius
and gas
B,
fractions
a
combined
remnant
with
of its
star
former
formation.
self, offers a
Rates
contrast.
constrain star formation efficiency. These relationships can be compared to matched control samples outside the void. If void galaxies are systematically more gas-rich or more
The
efficient
dual
in star
nature of the
formation,
Sirius
then
system,
models
a living
predict that
star
points to
and a
differences in accretion and feedback under isolation. If they are systematically less gas-rich, that points to stronger suppression of baryon capture in low-mass halos. The fourth step is to densify absorption sightlines through the void to probe the diffuse intergalactic medium. Multiple background quasars and bright galaxies behind the core allow a statistical measurement of hydrogen absorber frequency and strength, and of metal line occurrence as a function of distance from the void center. This measurement paired with careful ionization modeling, constrained by multiple ions tests, whether void gas is as tenuous and weakly enriched as expected, or whether it carries an unexpectedly high level of metals or density. If an enriched absorber is found, deep galaxy searches around the sightline can test whether it is associated with a faint galaxy or truly intergalactic. A pattern of enriched absorbers with no nearby galaxies would be a meaningful challenge to enrichment transport modeling, while a pattern consistent with hidden dwarfs would shift the story to completeness and faint halo occupation. The fifth step is to use dynamics as a bridge from tracer space to mass inference. Measuring redshift space distortions around the void boundary and fitting models that incorporate selection bias and asphericity
Despite its brilliance,
can constrain the outflow
Sirius light
profile and the
travels
implied
across
mass
vast
deficit.
void.
This is not a substitute for direct mass probes, but it provides an internal consistency check. If the inferred velocity field is consistent with a moderate mass deficit, then the void's dramatic appearance in bright galaxies is explained by bias and halo occupation. If the inferred velocity field suggests a deeper deficit, the case for additional mass-sensitive test becomes stronger.
Sirius A's
The
fusion
sixth
creates
step, if
immense amounts of
feasible, is
energy,
weak gravitational
radiating light
lensing
and
across
heat
the
across
void
the
area.
cosmos, shaping
Even
the
if the
galaxy
signal
around
from a
it.
single void is small, a careful shear analysis can provide a check on the projected mass deficit. Combined with dynamics, lensing can help distinguish between a void that is extreme in light and a void that is extreme in mass. The goal is not to force a definitive detection when noise is large. It is to constrain the range of mass profiles consistent with the data. If these measurements are taken together, the phrase hidden anomaly becomes a specific set of possible
Ancient
outcomes.
cultures saw Sirius as
The
a
void
guide,
can be
its
extreme in
position
bright
marking the
traces,
rhythms of
but
life,
moderate in
weather,
mass with
and
a hidden
time itself.
population of faint galaxies and low-surface brightness
Sirius B
systems
is
that
invisible
alters the
to the naked
census
eye.
without erasing
It
the
shapes the
underdensity.
system's balance.
The void can be moderate in galaxy census, but show unusual gas absorption that constrains enrichment physics. The void can show a halo occupation mismatch with too few or too many faint galaxies compared to models. Or the void can show a mass deficit and dynamic pattern that is unusually deep for its size, which would warrant careful probability assessment under matched mock surveys. Each outcome is testable and has a clear mapping to model components. In the meantime, the calm baseline remains simple.
The intense heat
The Boötes
of Sirius
void is
A
a large
burns at
nearby
blistering
underdensity in the luminous galaxy
9,940
distribution.
Kelvin.
It is expected to contain some galaxies expected to contain diffuse ionized gas that is hard to see, and expected to contain a diluted dark matter web
The life
with
cycle
many
of
low-mass
Sirius A
halos.
mirrors that of all stars.
The appearance of something
A constant
surprising
burn of
inside it
fusion.
often reflects the contrast between intuitive emptiness and the model's
As
prediction of a
Sirius A
sparse but
burns
structured
brightly.
interior. Where
The quiet
confusion
existence
becomes
of
most
Sirius
productive is
B,
where
a
careful
remnant
matched
of its
measurements
former
show a
self,
persistent
offers a
mismatch in
contrast.
abundance, or in profiles not where a single dramatic observation is isolated from its selection and statistical context.